Hi everyone, my name is Ivan Grohodkov.
Hey everybody, it's me, Lady Ada.
Okay, and then how does the future look for ULP?
Hi, we're excited to be here at Espressif DevCon.
Hi ESP, turn on the light.
How can I get started with IDF?
How we can start with Matter?
I love this question. If you want, there is right now that you can try.
Yes, so the service is already available.
Hello everyone, welcome to DevCon.
Nice to meet you.
Welcome to Espressif DevCon23.
Espressif DevCon23 is unmissable. See you there.
Hello world, my name is Yanis.
And my name is Ivan.
And we're thrilled to welcome you to Espressif DevCon23.
This is Espressif's second official conference, which is made by developers for developers.
After all the positive feedback on last year's DevCon, it was a no-brainer that Espressif's developer conference should become an annual tradition. So here we are with Espressif DevCon23. We're broadcasting live from Brno in the Czech Republic, where Espressif's European branch is located. For the next couple of days, we'll be sharing our technical know-how with a global developer community while shining a light on Espressif's latest projects, products and services.
The other aim of this online conference is to increase Espressif's engagement with all of you out there. We want the connection between the company and developers across the world to become stronger. We also want to hear your feedback on everything we do. So do let us know in the chat or in YouTube comments what you already like about Espressif and what you would like us to focus more on.
Now, let me give you a brief idea of the conference structure. The daily schedule of the conference is divided into 3 sections lasting more or less 2 hours each. In between these 3 sections, there will be 2 breaks, which we hope will make this event look less like a marathon.
After every presentation, there will be a 5-minute Q&A session where our speakers will answer your questions live. At the end of the second day, there will be a 30-minute general Q&A, a virtual roundtable if you like, where our panelists will answer any remaining questions from the audience.
So, ladies and gentlemen, boys and girls, without further ado, let Espressif DevCon23 begin.
We will kick off the conference with a keynote speech from none other than Espressif's founder and CEO, Theo Sui-An. Both Yanis and I have had pleasure working with Theo in Shanghai, but it's not just us at Espressif who know him well.
That's absolutely right, Ivan. Theo Sui-An is well known both to the developer community and the AIoT industry. Since establishing Espressif in 2008, his work has gained international renown for his leadership and his dedication to pushing boundaries in the IoT industry. So let's listen to what he has to say today.
Hello everyone, my name is Theo and I am the CEO of Espressif Systems. Welcome to the second Espressif Developers Conference. We are very excited to talk to you today about all the things that we have been working on since last year. First of all, we are happy to announce that we have recently crossed 1 billion aggregate chip sales. That means since the launch of ESP8266, we have shipped a total of 1 billion chips. This is a very significant milestone for any semiconductor company, not just because it's about the company, it's about the market and our customers. So in short, our customers are doing very well. In fact, we shipped about 200 million chips last year. We also predict that we will reach the next 1 billion chip sales in about 3 years' time. This target highlights the effectiveness of our developers-focused approach and the resourcefulness of our users. Since ESP8266 and ESP32, we have enabled millions of developers around the world to use wireless technology to create innovative connected devices. This year, we have successfully taken 2 of our chips, ESP32H2 and ESP32C6, to the mass production phase. So in addition to Wi-Fi and Bluetooth connectivity, we now also provide solutions for 802.15.4 radio, supporting Thread and Zigbee protocols. We also announced ESP32P4 early this year. It is an MCU-only chip with good computing power and a large number of I/O peripherals with plenty of GPIOs. ESP32P4 has our first multi-core RISC-V-based high-performance MCU with AI accelerating vector instructions support. We have deliberately not built connectivity into the chip so that the developers can have the freedom to choose whatever wireless standard that they need. We already have samples now for ESP32P4, and we can't wait to make them generally available to all developers to see what they'll build with them. While we continue to launch more and more chips, ESP IDF continues to support all our hardware, making it easy for developers to build their applications. It provides a seamless user experience, irrespective of what chips you are developing for. At Espressif, we understand that developers' experience are crucial to building a great product. The recently released ESP IDF supports ESP32H2 and ESP32C6, well along with additional Thread and ZigBee protocol stacks. We now also have a component manager for ESP IDF that helps all developers to not only use the various software components, but also contribute their own libraries to the benefit of the developers community. We see more than 20,000 downloads of these listed components per week. After the successful launch of the Metal protocol at the end of last year, we see a lot of excitement from developers in building devices with Metal support. The Metal protocol has the potential to simplify development and deployment, improve interoperability, increase security, and reduce fragmentation. It is our goal that all customers, irrespective of their size, can build Metal devices with ease. That's the reason why we have also become promoter members of the Connectivity Standard Alliance, CSA. We don't stop at providing just the Metal SDK supporting our chips, but also offer everything from device certificate pre-provisioning service to certificate assistance. For the developers who want to innovate at a higher level, we now also have ESP Zero Code Console offering, which provides a graphical interface to generate Metal-only firmware for building common types of devices. Our cloud software, ESP Rainmaker, continues to provide the ability for all to have their own private cloud, fully in their control, build all components of the IoT systems, the device, the phone apps, the cloud backend, and the dashboard effortlessly. We took it to the next level by enabling Metal ecosystem support in ESP Rainmaker. ESP Rainmaker is now the first customizable solution available, along which you can build your own Metal ecosystem and work with any Metal compatible device to add value to end users. Our public Rainmaker cloud and phone apps also support Metal protocol, and you can onboard any Metal compatible devices using ESP Rainmaker phone apps now. The recent advancements in AI with the evolution of large language models are highly disruptive for all technologies. Smart homes and connected devices will be no exception. The interoperability that the Metal protocol provides will help bring different devices together to take advantage of these AI-driven use cases. The use of AI in smart home and connected device segment will bring much better personalization, cost and energy saving, and drive more privacy-centric and voice-enabled use cases. So for such AI-driven use cases, the brain of the system will be distributed, and the device will have a role to play to run part of the AI algorithm locally. Our chips like ESP32S3 and ESP32P4 provide vector instructions to accelerate this edge processing. And our SDK like ESPDL provide the ability for developers to easily create, test, and optimize models. We have recently added TVM compiler support in ESPDL so that developers can bring other models to run on Espressif chips with ease. Last year, we also talked about the sustainability of our products and sustainability using our products. We continue to spend efforts on both of these aspects as we understand that IoT will contribute to climate conservation efforts significantly. You will continue to see power-efficient designs from us in hardware and software. As we always say in Espressif, our products are there to make you more expressive. You should be able to use the technology that we built with ease without worrying about nuances. We take these efforts to ensure that you can focus on your innovation. Through this developers conference, we would like to present to you what we have done and, more importantly, get feedback from you. I'm confident that you'll find this year's developers conference to be informative and inspiring. Our engineers have prepared many in-depth sessions covering all of the aspects that I've mentioned, and I encourage you to attend as many as possible. Thank you.
It is always interesting to listen to what Theo Svian has to say. So, many thanks for his speech this morning. Coming up next is Chen Xu, Espressif's Senior Engineering Manager in Shanghai. He will give an introduction to Thread, which is a low-power, low-latency wireless mesh networking protocol built on open standards with an open-source implementation. Thread addresses some of the IoT complexities such as interoperability, range, security, energy, and reliability. As a mesh network, Thread has no single point of failure other than the border routers.
Today, Chen Xu will introduce the fundamental concepts and advantages of the Thread network transport along with the main features of the Matter ecosystem. Additionally, he will delve into Espressif's Thread solutions, focusing specifically on our company's SoCs with Thread capability, the RTOS-based Thread border router SDK, and Rainmaker over Thread. So here is Chen Xu's presentation, which will be followed by his live Q&A session. He will join us from Shanghai.
Hey everyone, this is Chen Xu from Espressif. Welcome to the talk. I'm the Senior Engineering Manager responsible for the research and development of Espressif solutions for Thread, Zigbee, and Matter. In this talk, we are going to dive into the details of the Thread network protocol and exploring how it works in the Matter ecosystem and learning about the Thread solutions that Espressif offers. So first, we will introduce the Thread. What is a Thread? In short, Thread is a low-power, secure, and IPv6-based mesh networking technology for IoT products. It's built on top of the existing 15.4 PHY and MAC layer, introducing 6LoWPAN and IP routing features, providing a standard IPv6 interface to the upper layers. So currently, Thread supports a single OQPSK file operating at 2.4 GHz and 250 kbps data rate. The Thread 1.1 is based on the 15.4 2006 version, and since Thread 1.2 and later, it requires some new features defined in the 15.4 2015 version, such as the coordinated sampled listening feature, which supports some lower power consumption device types. So I will talk some more details later. Now let's talk about the 6LoWPAN layer. Thread, based on 15.4, provides an IPv6 interface to the upper layer. However, the IPv6 frame is large, with 1,280 bytes MTU and a 40 bytes IPv6 header and a 4 bytes UDP header. Yeah, so you see the overhead is very big. So to deal with this overhead, the 6LoWPAN adapter layer is introduced to fragment and reassemble IPv6 packets to and from 15.4 frames. The next layer is IP routing in Thread. So before we look into the routing protocol in Thread, let's first take a look at the Thread networking topology. In a Thread network, there are several different types of devices. In this diagram, The devices with blue color are all 4-thread devices that implement the 4-thread function. They could be router devices or REED device. So here the REED device means it's the device which can work as a router, but they don't act as such at the moment. The devices in black color are minimal thread devices, which only implement the minimal threaded functions to be an AND device. So here, the minimal threaded devices cannot be router. They can only be the AND device. This AND device could be the power device or some sleepy AND devices. So thread is a true mesh network, meaning any router devices that can hear each other, and they can maintain a routine link. So here is the leader. Leader is a special router device. So first, leader is a router, but it's a special router device. And each thread network has only one leader. The leader is responsible for managing other routers, aggregating and distributing network data within its thread network. The border router is another important role in a thread network. It provides connectivity to other IP networks. In a thread network, there could be multiple border routers, and any device with a non-thread network interface, like the Wi-Fi or Ethernet, can work as a border router. And each thread network has a set of network parameters. It's known as a dataset. For a device to join the network, it needs to know the network key or the entire dataset. The thread protocol defines a commissioning process to securely commission a new thread device to the network. But in some real use cases, the dataset can also be given to the device via some out-of-band method, such as the application layer commissioning process. So once a thread device has got the network key or the entire dataset, it can start joining the network. This process involves the mesh link establishment flow. In short, we call it MLE. So the MLE protocol defines how the links are established in the thread network and how network data is distributed. So there are several kinds of network data in a thread network. It includes the leader data, like the leader address, partition ID, partition weight, and some other network data includes the on-mesh prefix and some addressing and routing configurations. The MLE is actually carried over UDP. This is a generic format of an MLE message. So in this message, there is a security header and a command ID with the TLV-based payloads. When a new device joins the network, it starts with the attach process, which is also known as the child-to-parent link. This is done through the MLE messages and involves 4 steps, from the parent request, parent response, to child ID request and child ID response. The parent request is a multicast message. The device will send and to find the router or REED who can act as its parent. Then the subsequent child ID request and response are used to complete the attach process to get a child ID and to establish the link. Then the device finally joins the network as a child. So it's the first link type. We call it the child-to-parent link. The second link type is the route-to-router link. The routers can establish links with other routers as long as they can hear each other within a single hop. This is done through 3 MLE messages. They are the link request, link accept, or we can put the link request and accept in a same one message. With these links, the thread devices in a same network could form the mesh topology. And the 4 thread devices, the FTD can switch roles between child and router based on the network's requirement. So any devices will join the network as a child, but the FTD will join as REED. They can be upgraded to the router to extend the connectivity or support new devices join the network. For example, when a new device wants to join, but there's no router which can help, so the REED will upgrade itself to router and support this device to attach to the network. Similarly, a router may downgrade to a child based on certain conditions. For example, when there are enough routers, but not so many children, or when the other routers are enough to replace its router role. So a router device may downgrade itself to a REED. But of course, it can still upgrade to a router whenever necessary. In Thread network, all messages are protected by AES-CCM encryption and authentication with 32-bit MIC. The MLE messages are all protected using the MLE image security, and other messages will use the 15.4 layer frame security. So here is the exception for the commissioning messages. So here comes to the addressing part. Each thread device has several IPv6 addresses using different scopes. The scope includes the link local, which is with a single hop communication. And the RAM local scope is within the thread network. We can also call it the mesh local. And the global scope is used to communicate with the devices out of its thread network. The mesh local addresses are used for routing in thread network. There are 2 kinds of mesh local addresses. The EID, the endpoint identifier, is a unique identifier which will not change even the network topology changes. But the routing locator, the alloc address, will change based on the topology because the alloc is generated by the router ID and child ID. So let's see an example. So we have 2 routers with the router ID 1 and 2, and each router has 2 children. The router ID 1 and children ID 1 generates an alloc address 401. And together with the mesh local prefix, it could generate an alloc address used in the thread network. So here, the mesh local prefix is one of the parameters in a thread network data. After we introducing the network topology, MLE, and addressing scope, now let's back to the routing part. The routing protocol in thread network is the shortest path and any-to-any routing. The routing path is among routers, and the parents will help their children to receive and forward the messages. And here in a thread network, there are no more than 32 routers, which means that for biggest thread network, the biggest router number is 32. And each router in a thread network has a link table and a route table. The link table includes all the neighbor routers and the incoming and outgoing quality of the link. So in thread, the link quality is based on the signal stress. Since there are up to 32 routers in a thread network, the entries in the link table are up to 31. Let's check this example. There are 5 routers, A, B, C, D, E, and B, C, E are A's neighbor, so they are in A's link table. And A also has a route table, which includes the next hop and the cost to all other routers. So in A's route table, the next hop for B, C, E are all themselves because they are only one hop. But the next hop for D is E. So any messages from A to D, A will send to E first, and E will help to forward the message to D. But why don't A choose C as the next hop for D? Because the both are two hops. This is because that the A knows the link quality to C is not as good as to E. You can go back to the link table. You can see that in the A's link table, the C's link quality is not as good as A and B's link quality. So in this case, A will consider the cost to C is higher than to E. So A will prefer to choose E as the next hop to D. And all the thread routers will advertise their route information periodically. For each destination, the router will determine the path cost through each neighbor and select the neighbor with the minimal path cost. Route table is dynamically updated according to the network topology and link quality. So this is the thread routing protocol. Then let's go to the thread, another benefit of thread, which is no power. The thread no power is achieved by some sleep and device types. For example, a sleepy end device, which can sleep for most of the time and wake up to query messages via data request, is defined in the 15.4. The wake up period depends on the application requirements from seconds to hours. Since thread 1.2, it introduced a new sleepy end device called the synchronized sleepy end device, which does not need to send any packets after waking up. Instead, it just turns on the IF and receives. So to receive a message, consume less power than to send a message. Of course, the child and the parent should be synchronized on the listening window. This is done by the coordinated sampled listening feature defined in the 15.4 2015 version. So this is how a thread device to achieve the low power consumption. Then we come to the threadable router part. It's a very important role in the thread network. It connects the thread devices to other IP networks. To achieve the bidirectional connectivity, the border router will generate the OMR prefix. It's the off-match prefix, and advertise it in the thread network data. Each thread device will add a global unicast IPv6 address from the OMR prefix. In the meantime, the border router will advertise the OMR prefix by sending a router advertisements to the Wi-Fi network, in which it includes the route information option. So the other Wi-Fi devices know which is the destination to send messages to a device with the OMR prefix. And similarly, border router send a prefix information option, the PIO, in the router advertisements to Wi-Fi networks. And the Wi-Fi devices will add a unicast address based on the Wi-Fi prefix. And also the border router will include this Wi-Fi prefix in the thread network data as an external route. So the thread devices will know if any devices want to be sent to the Wi-Fi devices, they can send the message to the border router, since it supports the external route. Then the service registration and discovery is another important feature of thread border router. It makes it possible for devices in thread and other non-thread networks to discover each other using the DNS-based discovery. The border router implements the service registration server, advertising proxy, and the discovery proxy. All the thread devices register their services to the border router, and the border router will help to answer all the MDS queries from the other networks. If a thread device wants to query a service, it can also send a unicast DNS query to the border router, and the border router will help to perform a multicast query from other networks. Generally speaking, all the DNS query and responses in thread network are unicast, which means that the thread devices don't have to stay awake to receive multicast queries and answer by themselves. This helps to save a lot of power consumption compared to the other Wi-Fi or Ethernet devices. Multicast is also supported by a thread network, but it uses an optimized protocol called MPL, which is designed for the low power and lossy networks. The thread devices register their multicast addresses they are interested in to the border router, and the border router maintains a multicast listener table and performs the multicast forwarding. So any multicast messages come to the thread network that will use the MPL protocol. Yeah, as we already discussed, the thread provides the IPv6 interface to the app layers. However, there are some limitations on the availability of IPv6 connectivity in the public IP networks. To enable thread devices to connect to public IP networks and facilitate the end-to-end communication between thread devices and cloud services, the border router needs to implement the DNS64 and NAT64. These mechanisms perform mapping and translation between the IPv4 and IPv6 addresses, allowing the seamless integration of thread devices with IPv4-based networks. So here we also give an example. If we want to know the address of the Espressif website, we do a query, and we will get the mapped IPv6 address. And then we use this address to do the communication. Okay, then we come to the second part. We will talk about how thread works in a meta ecosystem. So you know thread is a network protocol. There are several applications that can work over thread, like the HomeKit, Weave, and Matter. Matter is currently becoming more and more popular. So here we take Matter as an example. Matter is an application protocol that runs over IP networks. Currently, it supports Ethernet, Wi-Fi, and Thread. These three networking protocols also provide the IP interface. In a typical Matter topology on the right, there are Matter over Wi-Fi and Matter over Ethernet devices, and a phone as the Matter commissioner and controller, and also the Matter over thread devices, as well as the thread border router. So it's a very typical Matter topology in the real life. The thread border router helps to forward IP messages between thread and non-thread networks. So all these Matter devices can communicate with each other end-to-end within the local network without the need to go through a cloud or any kind of gateway device. From the Wi-Fi to the thread, from the phone to the thread, or between two thread devices from different positions, these all can communicate to each other end-to-end. And in Matter, it uses the DNS-based service discovery, which is supported by thread border router as well. The Matter devices, whether they are from Wi-Fi or thread, can discover each other. The only difference is that the multicast DNS is used in Wi-Fi or Ethernet, while the unicast is used in thread. For example, when the phone app controller wants to find a Matter over thread device, it will send a multicast query in Wi-Fi network. Since the BR knows the service, which was already registered by one of the thread devices, then the BR will respond the query to let the controller know the thread device's address. And of course, when the controller wants to send a message to the thread device, it knows the route, as we introduced just now. So it will send the message to the border router first, and the border router will perform the IP layer message forwarding to the thread device. Meta also has a group feature, which is based on multicast. Once a thread device joins a Meta group, it will register the corresponding multicast address to the border router. The border router will help to listen and forward the multicast message. Of course, the suitable MPL protocol is used in a thread network for multicast. Now, the last part is about the thread solutions we can provide. Espressif offers hardware platform solutions for thread. Now we have two SoCs that support thread, which is 15.4, the ESP32H2 and ESP32C6. Both SoCs are production ready. The ESP32H2 is a BLE and a 15.4 combo SoC, while the ESP32C6 is a 3-in-1 SoC supporting Wi-Fi 6, BLE, and 15.4. So our customers can choose either the H2 or C6 to build Meta devices, Meta over thread devices. Moreover, by combining Espressif Wi-Fi and the 15.4 SoC, we can also offer thread border router and Zigbee gateway solutions. In these setups, one Wi-Fi SoC serves as the host, with an H2 used to extend the 15.4 interface. However, some developers may ask about using a single C6 to build a thread border router, but actually it's not recommended, as the C6 has only one IF path, which means the Wi-Fi and thread can't receive at the same time, leading to high packet loss rates. As a result, we recommend the two SoC solution for ESP thread border router, which ensures the good performance and the efficiency. The Espressif Thread SDK is built on top of ESP IDF and OpenThread, and both ESP32C6 and ESP32H2 are officially supported since IDF 5.1 version, as well as the Thread SDK and the border router SDK. And I also want to note that the C6, H2, and the ESP Thread border router solution are all Thread 1.3 certified components. And below are some useful links. The Thread SDK and the Thread examples are all in the ESP IDF itself. And we provide some additional border router production features and examples in the ESP Thread BR repo. If you want to build a Meta over thread product, the ESP Meta is the correct SDK. Now let's look into the ESP thread border router solution. It's an FreeRTOS-based thread border router solution, which is different from the commonly used OTBR POSIX solution, which is Linux-based. This means that the ESP border router solution is very cost-effective. It fully supports all the thread border router features, including the bidirectional IPv6 connectivity to both Wi-Fi or Ethernet, as well as the service discovery, multicast, and NAT64. In addition, it also provides some more production features, such as the Async update, since the solution involves two SoCs and requires the download of two matching formulas for OTA. So the SDK offers a mechanism that combines the two formulas into a single binary. With a one-step OTA process, the host SoC will automatically download the RCP formula to the 15.4 SoC during the initial boot. And the IF coexistence design is often a challenging aspect for devices which have multiple radios. So in our Bolalout SDK, we have the integrated hardware and software design, which offers the 3-wise PTA coexistence feature. So this feature helps a lot to simplify the complexity in the customer's application. And additionally, the SDK offers a user-friendly web GUI for easier configuration by the user. Moreover, the provided REST API are compliant with the APIs offered by the OTBR POSIX to ensure the compliability and the seamless integration. And finally, the Thread device can also integrate with Espressif's Remake cloud solution, which allows the Thread devices to be connected to the Remake cloud service via any NAT64-enabled Bolalout. This means that any cloud-based solutions, such as the remote control, OTA, and device management, all can be supported on the Thread products. The only requirement is the Bolalout has to support the NAT64 feature. Yeah, the end. So thanks for watching, and feel free to reach out to us for any further inquiries. Thank you.
Hello, everyone, and welcome to the Q&A session. So my name is Pedro Minatel. I'm developer advocate here at Espressif, and I will be the host for all the Q&A sessions. For this session, we have here Shensu. Hi, Shensu. How are you today?
Hi, hello. Nice to meet you. Yeah. Thanks for joining the session.
Yeah, so we have 2 questions here, and I would like to ask the audience as well, like to ask questions. So, and enjoy this opportunity to talk to our experts. So let's go to for the first question. Wi-Fi and Thread are all IP-based network protocol. What's the main difference, and what's the typical use case for Thread?
Yes. So you know, Espressif has been working on the Wi-Fi SoC for many years. And we started to work on and provide the Thread solution in recent 2 years. And yes, both Wi-Fi and Thread are all IP-based network protocol. And Wi-Fi is currently very widely used all over the world. And I think everyone's home has a Wi-Fi router. But Thread is pretty new to most of the consumers. Comparing Wi-Fi and Thread, so Wi-Fi is mainly designed for the high throughput and low latency use case, while Thread is mainly designed for the low power consumption and mesh network use cases. For example, we can have more than 200 Thread devices in a single network. Yeah. So regarding to the typical use case for Thread, we can already see many Thread-based devices on the market, like the lighting switch, plug, and many kinds of sensors, like the temperature sensor, occupancy sensor. Yeah, all these are not, the data rate is not so high. They just transmit some sensor data or some control messages. So these device types are mainly, I mean, Thread is a good choice. Yes.
Okay, thank you so much. And for the second question, I think, which is quite important for everyone. So the question is like, is Espressif Thread solution ready for production? So have any device on the market shipped with ESP32H2 or even the ESP32 CEST?
Yes, right. Actually, we already have customers' products on the market shipped with the ESP32H2. So H2 is Espressif's first FreeRTOS and BOE combo SoC. And we already have actually both ESP32H2 and ESP32C6 as well as our thread router solution, all have been granted the Thread 1.3 certified component certification. Yeah, which means that all these solutions are ready for production, and we already have some custom devices on the market are using our Thread solutions. And we also we do expect to see more Thread devices, as well as the Thread router devices will be on the market soon, which is based on our SDK and solution. Yeah,
I see. Thank you. So we have one question here directly from the audience, which is like, how is the memory run/flash overhead for OpenThread?
Okay, so for Thread, actually, normally we don't run Thread-only device. I mean, Thread is the IP layer network. Normally, we will have application network. I mean, the application layer run over the Thread. Let me give some basic number from the Meta over Thread use case. So for Meta over Thread, the flash size is normally around 1 megabytes for the firmware, and so which means that we may need at least 2 megabytes to support OTA. And for memory use case, it's around 250 kilobytes memory will be used for Meta over Thread. Yeah, but if we don't consider the application layer for Thread only, actually we have 3 types. We have the FTD, the full functional device, as we introduced in the session, and also the MTD, the minimal device. So the two will consume different resource. Like for the MTD, for the minimal Thread devices, it may just need around like 500 kilobytes flash and 100 kilobytes memory. Yeah, it's pretty small.
No, yeah, it is. So first of all, like, thank you so much for being here and answering the questions we had today. If the audience have any other question, we'll be happy to answer by the chat. So thank you again. Have a nice day, and we can now go back to the studio. Thank you.
Okay, thank you. Bye.
Our next presentation will be delivered by Mao Jianxing, the manager of audio team in Shanghai. Jianxing will talk about Espressif's official audio development framework and multimedia solutions. He will summarize the latest developments in ESP-IDF, and then will focus on the new features introduced in ESP-IDF and how they can be used to build multimedia solutions.
With this talk, our viewers will learn more about the structure of ESP-IDF, as well as its innovative features and application scenarios in different industries. Indeed, ESP-IDF empowers groundbreaking audio developments that make multimedia integration seamless and efficient. So, let's attend Mao Jianxing's presentation.
Hello, everyone. My name is Mao Jianxing, and my English name is Jason. I'm the audio solution manager at Espressif System. I'm glad to share my content with you today. Before we get started, allow me to introduce our team. Our team focuses on the depth research of audio, video, and image algorithm, design multimedia software development frameworks, and integrating artificial intelligence technology to develop multimedia products, solutions for smartphones, children's education, multimedia entertainment, and other fields. Today, I will share the 3 parts for you guys: marketing overview, and multimedia framework, and multimedia solutions. Let's look at the first part, marketing overview. Let's share what we call the multimedia products. First of all, it's an audio product or video product. It has the latest artificial intelligence, such as voice and image recognition technology. Its application scenarios include smart home, applicants, children's education, and life entertainment, and other aspects. It may be an upgrade of traditional products or a newly designed product. Among traditional products, smartphone appliances are the most typically. Let's take a look at two products. Smart washing machine, you can use voice control to easy operate and enjoy a smarter and more convenient laundry process. It can be integrated with the smart home system to realize remote control and monitoring of laundry progress. In addition to the traditional alarm clock, the smart alarm clock also has practical functions such as weather information, schedule reminder, and so on. It can set music as an alarm according to your preference to help you wake up easily. It has a voice control function, which allows you to stop the alarm without any switch. The best representative of the new product is the Wi-Fi smart speaker. It has a built-in smart assistant, which can provide you with information, play music, and control smart home device through voice commands. The speaker has a high-quality audio output, providing an immersive music experience and clear calls. It also integrates the various entertainment, such as integrate the intelligent QA, story explanation, weather forecast, etc., etc., to meet your needs. Another type is a smart toy, which are designed for children, focusing on safety and education. It has functions such as interactive games, story explanation, and children's sound to stimulate interest in learning. It can provide useful education content through voice interactive to help children developing social skills. In the field of the video, home security system is an important application scenario of audio and video. Whether you are at home or not, you can remotely monitor and control the system through your mobile phone application so that your family and property are always under security protection. Here are some our commonly used home safety products. The Smart Cat Eye is our security system first line to defense. It has a high-resolution camera, night vision, face recognition, and other functions. It can monitor the dynamic of the door in real time when you are not at home to ensure your family's safety. The home camera is an important part of home security system, covering key area of the home, such as living room, porch, and garden. The camera can provide the real-time video monitoring and round-the-clock protection so that you can pay attention to the safety of your family and the property all the time. The smart door lock is a new technology, especially Wi-Fi smart door lock. The smart door lock supports many unlocking methods, such as passwords, fingerprints, and mobile phone applications, which can help you avoid the harness of dealing with traditional keys. The high-resolution camera on the lock can monitor the unsafe people at the door in real time. And video of abnormal behavior will be transmitted to your home or grounds for safety door access management. Now, let me introduce our multimedia development framework. The multimedia software framework consists of 4 layers. protocol, middle-level API, audio and video codec, and hardware abstraction layer. The ADF offers basic elements, pipeline components, and button service, as well as Wi-Fi and OTA connection service. AEC comes from ESP-SR, which is remove echoes in the core and improves the audio and video core quality. The protocol includes ESP-RTC, RTSP, RTMP, etc., etc. The audio codec includes D711, AAC, OPS, etc., etc. The image codec includes Motion JPEG, MJPEG H264, etc., etc. The process includes resample, EQ, etc. This section will introduce the commonly used codecs, which include image codec, video encoder, and AAC encoder. The JPEG encoder is used to convert raw image data into JPEG format for transmission and storage. The original JPEG encoding has a no frame rate and use a lot of memory. We used the PIE instruction on ESP32 S3 to optimize the JPEG encoder, improving its performance by about 2 to 3 times. The JPEG encoder has the following features. Right here, the input support RGB 888, RGBA, YCB, YCR, green, YCB, Y2, YCR, Y2, and the rotation supports 0, 19, 180, 270 degrees. The table on the right is our performance test result. The QVGA FPS is about 54. The QVGA is about 40. Same as the JPEG encoder, the performance of the JPEG decoder has also been improved by about 2 to 3 times. The JPEG decoder has the following features. The output supports RGB 888, RGB 565 big end, and RGB 565 near end. The rotation supports 0, 19, 180, 270 degrees. The table on the right is our performance test results. The QVGA is about 70 FPS. The VGA is about 16 FPS. The MPEG-4 AVC is a video encoder whose original implementation is unsuitable for night CPU. We are reducing memory usage by modifying the code structure and optimization CPU usage to replacing time-consuming C code with faster Basori code. We aim to make it compatible with ESP32 S3 so that it can run efficiently on this platform. Currently, the following features are supported right here. The table on the right is our performance test results. QVGA resolution information, the input format is YUV422. The FPS is 10.66886. They're using 1 megabyte memory. AAC is commonly used for audio encoding in video stream, and we have developed the ESP AAC encoder. It supports the following feature. AAC low complexity profile is supported. The they separate support 8 kHz to 96 kHz. Mono and dual channel are supported. Bit per sample is 16 bits. The constant bit rate is from 12 kbps to 160 kbps and supports no ADTS header encoding. The table on the right is our performance test results. The memory used 42 kilobytes. Next, I will introduce the protocol in the multimedia application we have developed, such as ESP-RTC, ESP-RTSP, and ESP-RTMP. The first one is ESP-RTC we developed, which is a lightweight real-time communication protocol that is suitable for voice call, video call, and voice conference. The interface is straightforward and it offers a flexible API. The software structure is illustrated the diagram on the right. The main feature includes the STIP version is 2.0, transport layer support UDP, TCP, and TLS. The audio codec supports G711, A, G711U, and OPS. The video codec supports MJPEG and H.264. The green part of this picture in the function we are developing, such as WebRTC, ICE, and PRC. The ESP-RTSP protocol is developed by Espressif System based on the standard RTSP. It's an application layer protocol used for controlling the delivery of real-time data, such as audio and video, over IP networks. It used TCP or UDP as a transport protocol and typically operates on top of the RTP video stream. The ESP-RTSP is perfect for IoT applications that need real-time media communication with no latency, like video monitor and audio stream. The ESP-RTSP has those features. It supports RTSP version 1.0. It supports pusher, server, and client. Its public method have options describe, setup, play, tear down, and it supports the most popular RTSP servers such as EasyDraw. The last protocol is ESP-RTMP. RTMP is an Adobe protocol for real-time multimedia stream. It's used for live stream, interactive media, and video platforms. TCP is used with it, along with other protocols like AMF for the RTMP along for low latency stream and dynamic bitrate changes, making it suitable for real-time application like live video broadcasting, online games, and interactive web applications. The ESP RTMP is developed based on RTMP version 3. They have 3 roles: publish, RTMP push, player, RTMP source, server, RTMP server. The RTMP server that receives the audio, video, and data stream from the source and distributes them to clients or other servers. RTMP player that connects to the RTMP server to receive and play the live stream or interactive content. The RTMP published is the source of audio, video, or data stream, such as a camera or an encoder that capture and sends the content to RTMP server. The ESP RTMP support audio codec includes PCM, G711, AAC, and MP3. The image codec supports H.264 and the motion JPEG. In particular, the motion JPEG is not supported in the standard RTMP protocol. This section first discussing the application products of smart home, and then introduce the application solution we have already supported. Smart home, also known as home automation, utilize advanced technology to provide people with increased convenience, comfort, and security. Here are some common application scenarios for smart homes. The first one, home security. Smart home employ a range of security features, such as smart door locks, surveillance camera, motion sensor, and window sensor, allowing home owner to monitor their property remotely and remotely control access to their homes. The second one is smartphone applications, like smart washing machine, air conditioner, smart lighting, and coffee machine can connect to the internet and be remotely controlled. For instance, user can receive notification about the progress of laundry or start their conditioner before arriving home, or adjust brightness level based on natural light. The second one is voice assistance. Smart home can integrate with popular virtual assistants like Amazon Alexa, Google Assistant, or Apple HomeKit, enabling voice control for a wide range of connect device and service. Through smart home apps or voice assistants, homeowner can remotely control aspects of their homes, including security, lighting, temperature, and appliance, providing increased convenience and peace of mind. The following solutions showcase how using smart home technology can greatly enhance the overall quality of life and provide a secure and convenience environment for those residing in the home. The first solution is a video call, which can apply for smart door lock, surveillance camera, baby monitor, and other similar products. Our video call project is based on ESP-RTC, which supports motion JPEG and H.264 for image compressing, and AAC ops G711, etc. for audio compressing. It also uses the AEC, NS, and other technologies to improve the sound quality of calls. At the same time, it's a very lightweight project and can run ESP32 and ESP32S3 platforms. It also supports video call from device to device or from device to app and PC. In the video call project, the image connected by the camera will be encoded by motion JPEG or H.264 and transmitted to the receiver. After receiving the data, it will be decoded and displayed. At the same time, the connected audio data is processed by AEC and then encoded and transmitted to the receiver. Next, the data is decoded and played on the receiver. This project is a full duplex working model. In other words, it will have at most one image encoding, one image decoding, one image encoding, and one audio decoding at the same time. Its complexity is imaginable. So we can meet this situation by combining the performance optimization of motion JPEG or H.264 and AAC introduced earlier on ESP32S3. To view the code of the video talk project, please go to ADF's ESP-RTC project. In this picture, you can see the ESP-RTC init configuration process code. In this project, the buttons on the board have the following functions. Press the play button to call the special ID. Press the recall button to answer the incoming call. Press the mute button to end the call. Press the set button to enter the meeting room if the server supports it. You can adjust the voice volume by using volume plus or volume minus button. If you have an Android phone, you can also download ESP-RTC APK. After installation, configure your own server port, and then you can let the device and mobile phone have a video conversation. The picture on the right is a screenshot of the core of the mobile phone application. Here, we introduce an RTMP-based application solution that used the ESP32S3 Cover 2 developer board for live stream on YouTube. This developer board serves as the RTMP client using AAC for audio encoding and H.264 for video encoding to upload the captured video content on the YouTube server. This is the software diagram where audio and image go through every recorder and are sent to the server using RTMP protocol. The image on the right is a live scene on the computer. Video of 2022 Espressif Developer Conference is being played, which is ESP32S3 Cover 2 is capturing the computer screen and pushing it to YouTube for live stream. For the code of this example, please refer to ADF's RTMP project for instructing on how to use this project. Click here. You can view the live video by clicking here. In this application, you can also configure JPEG for image encoding. Also, this may reduce its university as most servers do not support motion JPEG video stream. The encoding speed of JPEG at different resolution is shown in those tables. The difference between those two tables is whether the camera outputs JPEG or YUV format data. In the application scenarios of smart door knocks, people used to have to go to the door to check and unlock the door after the doorbell rang. However, when the invitation of the remote control panel with the door lock, people can now unlock and view the visitor from anywhere in the room. And the door lock can connect multiple remote control panels. In the diagram on the right, the server has established a broadcasting stream and a chat stream with the two clients respectively. The chat stream is responsible for transmitting some control information, while the broadcast stream is while the broadcasting stream server as the channel for pushing audio and video data. The SSDP is in the diagram is used to discover the working of client and server, and it's allow for additional or removal of the panel as needed. In the actual application process, the server is a smart door lock, while the client is the door remote panel. This picture illustrates the initialize process of the RTMP server. It first call start RTMP server to start the RTMP server, and then creates the pusher and puller channels. On the panel side, it will first look at the server and join it, then open the puller channel. This is the software diagram. Well, data captured by the camera and the ADC is processed through AV recorder and then sent via RTMP to receiver. The receiver process to receive audio and video data for rendering. The code for this solution has not been released yet. If you are interested, please contact our sales teams. That's all. The above content is my presentation. Thanks for watching. If you are interested in any of the solution or have any questions, please feel free to contact us through GitHub or our sales teams.
Welcome to another Q&A session. And for this Q&A, we have here with us Jason. Hello, Jason. How are you today?
Fine. Hello.
Yeah. Okay, so we can go for the first question. The first question is, does ESP H264 supports H264 decoding?
Yes, we have optimized the H264 decoding on ESP32S3, and it is expected to release in the next big version of ESP H264 version 1.0. If you need to use in advance, you can contact us through the sales. Okay.
Okay, thank you. So the second question is, how large screen can be supported in the video intercom solution? What about the frame rate?
Okay. The frame rate is 40 FPS, and the resolution is 418 and 322.
Okay, thank you. So one more question here. Is it possible to make a smart speaker like Google or Amazon Alexa using ESP?
Yes, sure. Our ESPSR has been passed the certification by Amazon, and we also have some customers who has already mass production like that, something like the smart speaker. Yes.
Okay, I see. So some of the questions we will answer in the chat, and like if you have any other question about ADF and multimedia solution, you can ask in the chat. We will try to answer later. And yeah, so I'd like to thank you for your participation, for your talk. Thank you so much.
Thank you. Bye bye.
Yeah, and now we can back to the studio.
Next, we have the first lady of today's sessions. Wang Jianghui is an AI research engineer from Espressif's Shanghai office. The title of her talk is Customizable Speech Command Recognition on ESP32S3. This model runs offline in real time and can be easily customized. The talk will cover the model's structure, performance, and decoding method. Then, Jianghui will tell us how exactly it can be used for adding customized commands.
ESP32S3 has been designed specifically with AI applications in mind and has wireless communication, AI acceleration, and security features. Compared to the ESP32, ESP32S3 also has faster external memory interfaces. Application use cases such as online or offline voice assistants and other voice-enabled devices can be easily built on ESP32S3 using Espressif's SDKs, components, and solutions. So let's take a look at Jianghui's presentation and learn specifically how we can build customized speech command recognition on ESP32S3.
Hello everyone, my name is Jianghui Wan, and I am an AI research engineer here at Espressif. And our AI team works on a couple of speech-related projects, from speech enhancement, speech denoising, speech recognition, and etc. And today, I'm going to give you a talk on our customizable speech command recognition system that is currently supported by ESP32S3 series boards. And I hope by the end of this talk, you will have a general idea of how our system works, how to use it, and how to customize it for your own needs. Here is a chart of our entire pipeline. So the input to our speech recognition, speech command recognition system could be either directly from a microphone or from some pre-recorded audio files. And the input audio will first go through a audio front-end component. The audio front-end component has a few algorithms that applies audio enhancement to the input audio signal. And the enhanced audio will then be fed into our wake word engine we call WakeNet. The wake word engine is always listening until a wake word is detected. And once the target wake word is detected, the wake word engine will go to a standby mode and our speech command recognition model will be active. The speech command recognition model will listen to the audio after the wake word. And once a predefined speech command is detected, it will output the corresponding speech command. Currently, we support both Mandarin and English speech command recognition model, but only one model can be active at once. They can be switched or selected before you flash the program onto the board. And I will give a tour on how to do model selection in a small demo later. The detected speech command ID, there is an option to speak out this command via a speech synthesis system, a TTS model. Currently, only the Mandarin TTS model is supported and the English model is under development. The detected speech command can then be sent to any post-processing as you like, such as to control your smart home appliances from your music speaker to air conditioner. To sum up, In order to perform speech command recognition, a wake word must be spoken first. And once the wake word is detected, you can speak as many speech commands as you like until there is a period of silence that is long enough to trigger a predefined timeout. The predefined timeout is normally set to 5 seconds to 6 seconds, depends on the use case. So as shown on this graph, WakeNet will be actively listening until high ESP is spoken. Once it detected high ESP, WakeNet will go to a standby mode, and Multinet will be active. Multinet will be able to output the speech command ID from a series of speech commands: increase the temperature, turn on the lights, turn off my soundbox. And once there is silence that is long enough to trigger the timeout, Multinet will be disabled and WakeNet will be active again. Next, I will introduce each component in our system individually. The first component is the audio front-end, AFE component. Here is the workflow of our AFE component. Since the speech command recognition system is normally used in an indoor environment where exists a lot of room echoes or reverberations, therefore the first component is the acoustic echo cancellation component. The audio input first goes through the acoustic echo cancellation system, followed by a noise reduction system. The noise reduction system performs either blind source separation or noise suppression, depends on the microphones that are being used. Blind source separation is used in the case of dual mic, and noise suppression is used in the case of single mic. The last component of AFE is voice activity detection, filters out part of the audio that does not contain active speech. And the filtered audio is then fed into our WakeNet. Of course, if you are using this system in an environment where exists almost no background noise or room echoes, you always have this option to bypass all these components to get a further speed up. The second component in our system is the wake word engine, WakeNet 9. Wake word engine is a crucial part in our system as it tells the speech command recognition model when to start listening. WakeNet 9 is built upon a neural network structure and it supports up to 5 wake words at the same time. We first extract audio features from the in audio. The audio features that we're using is called melt-frequency capture coefficients, MFC. It's a type of feature that is specifically designed to model how human ears perceive speech signals. That is, to put more attention on the lower frequencies and less attention on the higher frequencies, just like how human ears work. The extracted MFCCs is then sent to the neural network, and the neural network acts like a classifier that classifies the input features into wanted word class or unknown word class. The unknown word class may contain other words or just any kind of background noise. In the case of multiple wake words, let's say, for example, 5 wake words, the neural network works like a multi-class classifier that classifies the input features into 6 classes, 5 wanted words and an unknown word class. More specifically, WakeNet 9 uses a dilated convolution model structure. It is a rather small model with less than 300K parameters, and the average running time for a 32 millisecond frame is 3 milliseconds. The reason that it is measured of 32 milliseconds is because WakeNet 9 produces 1 classified result every 32 milliseconds. And during runtime, it uses the average results over a few frames to get a final reliable results. This table shows the detection accuracy of WakeNet 9 on Alexa dataset at a false alarm rate 1 at 12 hours. In other words, this model is false triggered once every 12 hours. The first column here, distance, is the distance between the audio board, the audio source and the board. And when the board is 1 meter away from the audio source, WakeNet 9 is able to achieve 98% accuracy in a quiet environment. And if we add additional stationary noise to the audio source at an SNR of 4 dB, the WickNet 9 is able to achieve 96% accuracy. And if we add additional speech noise at an SNR of 4 dB, WickNet 9 is able to achieve 94% accuracy. If we move the board further away from the audio source from 1 meter to 3 meters, the performance of WickNet 9 is not affected. The third component of our system is the speech command recognition module, Multinet 6. It is activated once a wake word is detected, and it outputs the command ID when a speech command is spoken. Here is the workflow of our speech command recognition module. It consists of 2 major branches. Let's look at the upper part of this graph first. Similar to WickNet 9, we are extracting MFCC features from the input audio, and the extracted features is then sent to a neural network. We're using a conformer-based neural network structure for Multinet 6. I will add more details about this model structure in a few slides. Now let's look at the lower part of this graph. In the blue box is a list of predefined speech commands with their corresponding command IDs. For example, we have command ID 1 associated with the sentence turn on the lights, and command ID 2 associated with the command decrease the temperature. This list was then sent to a command FST. FST is the abbreviation for finite state transducer. I will add more details about this structure in a few slides as well. It is okay for multiple commands to have the same command ID in the predefined command list. For example, we can have decrease the temperature is too hot and make it cooler in the command list, and they can all have the same command ID too. During runtime, you can speak any of these 3 sentences, and the system will be able to output command ID 2. This feature gives you the flexibility to use different phrases to convey the same intent. The output of command FST works jointly with the output of Multinet 6 to get the final results, whether there is a command, a predefined command in the input audio or not. Now I will touch on the model structure of Multinet 6 and finite state transducer briefly without being too technical. The model structure of Multinet 6 conformer is shown on the left. It is a very popular used neural network structure nowadays in speech recognition tasks. It uses a combination of feed-forward layers, convolution layers, and multi-head self-attention layers. And it is able to achieve the state-of-the-art performance in speech recognition tasks. On the right is the finite state transducer that is built upon a list of 4 commands. Command 1, turn on the light, command 2, turn off the light, command 3, decrease the temperature, and command 4, increase the temperature. The resulting finite state transducer has 7 states here in circles. And the arrows means that we can travel from one state to another. State 0 is the starting state, meaning that we can travel to any state from here. And state 6 is the final state, meaning that we have successfully decoded one command that is represented by a path. We will use the first command, turn on the light, as an example. As highlighted in orange here, we can travel along the path from state 0 to state 1 to state 2 to state 3 to state 6 to finish this command, turn on the light. And note that we also have the second command, turn off the light here. So when the speech recognition model outputs the first token turn, there are 2 possible commands, turn on the light or turn off the light. And once the speech recognition model outputs the second word on, the only possible command is turn on the light with the command ID 1 here. So the FST works jointly with the output from speech recognition model to constrain the output of a speech recognition. In other words, we are actually limiting the searching space of speech recognition model to those predefined commands. So the entire system will output either a command ID or nothing. This FST can get a lot more complicated if there are tens or hundreds commands in the command list, but the idea behind it stays the same. Multinet 6 has around 3.8 million parameters, and the average running time per 32-millisecond frame is 12 milliseconds. Here in the table is the word error rate of Multinet 6 compared to our previous version of Multinet 5 on two open source datasets, LibreSpeech and AI-Share. LibreSpeech is an English dataset that contains reading audiobooks, and AI-Share is a Mandarin reading dataset. Word error rate here is the commonly used evaluation metric that in competition has. It is the summation of word insertion, word deletion, and word substitution. Since it is an error rate, the lower the better. The -en and -cn here represents the English model and Mandarin model, respectively. And as we can see from this table, Multinet 6 is able to outperform Multinet 5 by 7.5% in LibreSpeech and 4.3% on AI-Share. This table gives the speech command recognition rate on our internal dataset. Multinet 6 EN is able to achieve 96.8% recognition rate in a quiet environment. And if we add additional stationary noise, it is able to achieve 87.9% recognition rate and 85.5% recognition rate with additional speech noise added. The Mandarin model shows a similar behavior. It achieves 98.8% accuracy in a quiet environment and 88.3% accuracy with stationary noise added and 88% accuracy when speech noise is added. Besides these two models, we also released a Mandarin model that is specifically targeted at air conditioner commands. We name it Multinet 6-EN-AC here on the last row. Although it has like 1.7% recognition rate lower than Multinet 6-CN, it is able to achieve 95.1% and 96.8% recognition rate when additional noise is added. Our team is currently working on the next generation of Multinet 7. It has not been released yet, but I will give you a peek into our progress so far. The general workflow of Multinet 7 stays almost the same as Multinet 6. The major difference here is that we are changing the conformer-based model structure into a newer one called ZipFormer. I won't go to details about the model structure today. If you're interested, you can look up the references, or we will publish a detailed documentation once the Multinet 7 is ready and released. Here is the performance of the English Multinet 7 compared to the previous version on our internal test set. It is able to outperform Multinet 6 by 1% in a quiet environment and 1.5% with additional stationary noise added, and 2.6% higher than Multinet 6 when additional speech noise is added. Moreover, it has 1 million less parameters than Multinet 6, which means that it consumes much less memory and runs faster on board. This is an experimental result, and we are currently working on testing the model, finalizing it, as well as building the Mandarin one. With all those technical stuff being said, next I will show you a small demo on how to use this system on ESP box using WeakNet 9 and Multinet 6. We have a few working examples published on our open source repo ESP Skynet, from weak word detection to speech command recognition. And in order to run those commands on ESP Skynet, you will need a few things first. First is an audio development board that comes from the ESP32S3 series. We recommend you to use Cover 1 or Cover 2 for best experience. The second is a USB cable that works with the board. It could be a Type-C cable or micro USB cable, depends on the board you are using. And the third is a PC that runs Linux for development. On the software side, you will need to clone the latest ESP Skynet repo, which also uses ESP-SR as a component. You do not need to download ESP-SR separately as it is already included in ESP Skynet. You will also need to install the ESP IDF and make sure that it is the correct version that is recommended in ESP Skynet. Next, I will show you a demo that runs on ESP Box. It is basically the same as the example in ESP Skynet with some additional screen display to give you a better visualization. The first step is configuration and flash the program onto the board. I'm sure that you are pretty familiar with this process if you have worked with any ESP project before. So first, we're going to set the target to ESP32S3. And next, we will need to use menu config to select the models we want to use. Today, we're going to use the English Multinet 6. Once the configuration is saved, we can now flash the program onto the board by using idf.py flash. If this is the first time you are building this project, it might take some time for the program to build. So I'm going to skip this today. Now let's look at how it looks on the ESP box. Hi, ESP. Turn on the light. Increase the temperature. Turn on my sound box. As we can see from the video, the system is able to pick up a series of speech commands once high ESP is detected. And if we don't say anything for a while, it will go to standby mode and waiting to be woke up again. Next, I will show you how to add some new commands as well as modify the existing commands. You will be able to find this piece of code in our ESP Skynet example. This is basically how we build a multinet. To add a new command, we will use the function ESP-mn commands add. The first input argument is the command ID, and the second input argument is the command sentence. Here we are adding two new sentences, command 50, turn on the kitchen light, and command 51, shuffle my playlist. We also want to change the existing command by using ESP-mn commands modify. We're changing turn on my soundbox into turn on my speaker. And at last, we're going to use ESP-mn commands update to apply all these changes we just made. After reflashing the program onto the board, we can now test how it works. Hi, ESP. Turn on the kitchen light. Shuffle my playlist. Turn on my speaker. Turn on my soundbox. we can see that the model is now able to pick up the two new speech commands that we just added. And since we changed turn on my soundbox into turn on my speaker, it can no longer detect turn on my soundbox anymore. I encourage anyone that is interested in this project to try out our examples on ESP Skynet. And if you encounter any problems along the way, please feel free to contact us and we are willing to help. At last, I'd like to share with you the next steps of this project. In the near future, our team will be mainly working on two things. The first thing is that we're aware that there are a lot of needs of using customized wake words other than just high ESP or high listening. Right now, we need around 20K pre-recorded wake word sentences to train a new wake word model. And this is both like time consuming and budget consuming. So we are looking at alternatives to reduce the burden of manual data collection. And the text-to-speech engines nowadays is capable of produce natural human-like speech with a diverse collection of speech voice. Therefore, we are planning to utilize such a TTS engine to reduce the amount of real data required. The second thing that we're going to work on is Multinet 7, as I shown before. Both the English version and the Mandarin version will be released soon, so stay tuned. Here is a list of references for this presentation that you might find helpful. And please ask questions if you have any.
And now we are back to another Q&A session. And now we have Chunhui here to answer your questions. Hey, how are you today?
Good, how are you?
Yeah, I'm good, thank you. So the first question is, how can we train model to include new keyword?
We currently do not open source the training code of our pipeline, but we do offer the service to add new keywords to your system. And there is so because right now we do need some amount of pre-recorded keyword recordings. So whether it is recorded by you or recorded by us is negotiable. And if you are interested in building a wake word model with your own keyword, you can reach out to us offline, and we have a mature process of how this is going to be moved forward.
Okay, and how is the best way to contact Espressif for that? It's by sales?
You can, yeah. The best way to do is, I mean, you can always just leave a message on our GitHub repo. That's the quickest way that we have ESP Skynet or ESPSR, and that's I'd say that's the quickest way to get to us.
Okay, thank you. So now for the second question. Do you have available the right tools for implement the other languages than Chinese or English?
I think it's similar to our WakeNet engine that we currently do not open source our training code. And if you are interested in other language for speech command recognition, it needs a huge amount of data for training the base ASR model. So if you do have that data, you can, the same as the previous question, you can reach out to us and we can discuss about the next steps. Yeah.
Okay. So third question, is it possible to add speech command recognition using FST for other languages than like Spanish? How and which tools? Sorry.
I would say that if you want to use speech command from another language, such as Spanish, which we don't currently support, the major problem is that the speech command recognition model requires a base ASR model, and the ASR model needs to be trained with a lot of data that's from the source language. I would say there is a hacker way to do that. If you can find the Spanish sentence that sounds somehow similar in some English sentence, you can always try to kind of encode your Spanish sentence in English and to see how that works. But I cannot guarantee the performance though.
I see. So I think we have time for one more question. So would MultiNet consider language model to correct or increase accuracy to ASR?
I will say yes and no. We definitely did try to use an external language model on top of our ASR model. The thing that we found before is that it adds a lot of, not a lot of, but quite some additional computation, as well as the language model itself it has a lot of parameters and needs to be saved in the board, right? So with that being said, the performance improvement from adding an external language model we cannot just make that trade-off, right? It doesn't worth it to add additional computing resources and memory resources for just a little bit performance improvement. So we went forward with the FST approach. But who knows, in the future, maybe there is going to be some new language model that is so light and so efficient, and we definitely will try that out.
I see. So I think we do have time for one more question. So this will be the last one. So how much ESP32S3 CPU load / memory needed for voice recognition?
I'm a little bit confused by the term voice recognition here. I mean, does it mean word recognition or speech command recognition? But either way, it also depends on which board you're using. Like ESP32S3 box is definitely different than an Corvo box, right? And we have all this documentation of our memory consumption and the RAM consumption in our ESPSR repo.
I see. So thank you so much for answering the questions and for your talk. Thank you so much.
Thank you.
And now we can back to the studio.
All right, who's coming up next? It's Jeroen Domburg, Espressif's Senior Software and Technical Marketing Manager. His talk is entitled Bit Scrambler, a solution for out-of-order bits. And we all have a few of them, don't we?
Oh, we certainly do. Story of my life.
That said, Jeroen's presentation is about a new peripheral in ESP32P4. This peripheral is called Bit Scrambler, and it is a programmable device integrated into the DMA stream. As such, the Bit Scrambler can do really fast bit manipulations for the data that is being transferred in and out of memory with the existing peripherals.
So with more than 20 years of embedded experience, Jeroen is closely involved in the software and hardware design of Espressif chips. So this guy really knows what he's talking about. To put it simply, he works on Espressif chips and they help them make their magic come to the fore. Espressif's announcement of ESP32P4, which is a high-performance MCU with numerous connectivity and security features, caused quite a sensation when we revealed it last January. So I can't wait to hear about the new Bit Scrambler peripheral that goes with it. And Jeroen, the virtual stage is yours.
Hello everyone, my name is Jeroen Domburg. I work at Espressif Singapore nowadays and I do all kinds of stuff, amongst which is to give a presentation to you guys about the Bit Scrambler. As it says on the slide, the Bit Scrambler is a solution for out-of-order bits, and how that works exactly I will dive into. So first of all, a few caveats. This is about a peripheral for the ESP32 line of series that is not out yet. This is a tech preview. If the peripheral gets out, then it'll be in the ESP32b4 initially. However, that's an if and not a when, because we haven't silicon tested yet. So for all we know, the bit scrambler, if you turn it on, might just let out a magic smoke or something. We don't know. We're gonna figure that out. We can already tell you what it'll do if we get it to work. Also, a few things about the tooling here. I'm going to show you a few programs that are bit scrambler programs. The exact details of that are also not entirely worked out yet. We think we have it more or less down, but that might also change. So this is effectively the disclaimer. So with that out of the way, what is the use case for a bit scrambler? What practical problem does it solve? Well, the thing is that ESP32 chips always have had lots and lots of peripherals. So this is a block diagram of the ESP32b4, and you can see that there's a lot of peripherals that are non-single use. So you can prod them in order to do other things than that they are actually made for if you really need to. With all that, you could probably control like 90% of all interface needs, sensors, other microcontrollers, other things. But that's only 90%, and we would like to improve that number at least a little bit. So what exactly am I talking about? You need to, what's in the 10% that we're trying to get? Well, for instance, this is a real-life example. A customer came to us with some sort of unknown chip. I think it even was internal. I'm going to say it's a camera. I don't exactly know. The trick was that the interface to it, the data that is sent to the ESP, was in a weird SPI-like format. So just like SPI, if you know SPI, it has a clock line that just goes up and down. That's the clock. And on that clock, every time the clock goes up, there's one bit being sent out, and that happens 8 times, and then the ESP receives a byte. So that is not exactly how the camera works. The camera has 3 of those data lines: one for red, one for green, and one for blue data. And each single one of them sends out 1 bit per clock cycle. So it is not impossible to connect this to an ESP32. For instance, we have quad SPI, which is SPI using 4 data lines. It sends one nibble every clock, so 4 bit. This generally is done to make everything faster. You only need 2 clock pulses in order to send a byte and not 8. So this would kind of map to the current device. Namely, we could just connect the red line to D0, then the green to D1, and the blue to D2, and then we have a D3 left, which will just tie to ground or something. And the clock can go to the clock. And this is physically compatible, and also logically compatible, because we receive data on multiple lines every time the clock goes high. So the only issue is that if you do it like this, the way the data ends up in RAM is going to be all cattywampus, because the quad SPI is intended to receive nibbles at a time, and it receives 3 bits at a time. So if you now want to process this data, you first need to get all the reds together into 1 byte and all the greens into 1 byte, etc., which is a problem, at least for those people that was. Another example, something a little bit less obscure. So those SPI LCDs, right? They usually have the SPI ports, which consists of data, clock, and chip select. And they also have a DC line, which is a data or command line. The idea is that if you do an SPI transaction with that high, then you're sending a command, and if it's low, it's data, or the other way around, I don't remember. So it effectively looks like this. So if I send some sort of transaction with the DC line low, then it's data, and if it's high, it's interpreted as a command. So a command is, for instance, turn on the display, while data is, okay, this pixel needs to have RGB 1, 255, 1, something like that. So this is all very, very nice, and the ESP has absolutely no issue controlling this. However, some displays work in what's called a 9-bit mode, and the idea is that they get rid of that data/command line. Instead, what they do is, rather than sending bytes, they want you to send 9-bit values, and those are the same as the bytes, but the very first bit is the DC indicator. So if that is low, then it's data, and if it's high, it's a command. That's all nice and well, but that means that all of a sudden we need to send 9-bit values. Well, SPI doesn't care. SPI just reads data from memory and sends that out of the SPI port. However, it does mean that we now need to put 9-bit values into memory that is byte-wise oriented, so 8-bit in width. So you would get something like this if you were to look at the memory. You would get a pattern that's shifting. And again, it is possible to do this using an ESP, but it is not very nice to do. So as I said, it's possible. You simply reorder the bits. It's like trivial, right? And then you actually write it. So this is a little bit of code that reorders 3 bits in a byte. And then you figure out that it takes 6 instructions, one of them is a branch, in order to reorder a bit. And this is on a fast RISC CPU, but still 6 instructions per bit. That is a fair amount of time that you're just swapping around bits if you want to send, for instance, a picture to an LCD or something. So maybe we should do something about that. Maybe we should have some sort of accelerator, possibly. And this is exactly what the bit scrambler is. The bit scrambler is, as it says, a bit parallel, very large instruction word programmable state machine in the DMA path. So what do I mean by that? Well, let's start with the DMA path. The ESP32P4 has a bunch of peripherals that use DMA in order to fetch their data from memory and send the data back. It actually has more than the ones circled around, but these are the peripherals that you generally would want to use with the bit scrambler. The DMA path works like this. If, for instance, an SPI device wants to send some data rather than ask a CPU to manually put that in, you give it a certain block of memory, and the DMA interface is responsible for fetching that data and sending it to the SPI device, which then sends it on to the actual device attached. If you want to read from an SPI device, the same idea, but the other way around, data gets sent from the SPI peripheral to memory. So now you can introduce a bit scrambler in these paths. In this presentation in general, I'll be talking about the path from memory to a peripheral, like, for instance, the SPI peripheral. Everything also goes for the other way around. For if you want to send data from a peripheral to memory via the bit scrambler, that's possible. And it's actually even possible to do memory-to-memory transfers via the bit scrambler if you want to scramble your bits without having to send them to an actual device. So what does a bit scrambler look like? Well, it kind of looks like this. It has an input, it has an output. These are the things that go from memory to the peripheral, or, as I said, from a peripheral to memory, or even from memory to memory. And there's a little, let's call it a CPU in that block. And that CPU runs a little program. And as an example program, just to give you an idea what it looks like, let's start here. So you first see the read 16 instruction, and as it says, it reads 16 bits from the incoming DMA data. It then uses a set command, and what the set command does is it routes one of those bits to an output bit. So in this case, in the output word, bit 0, you'll set that to whatever value the bit 0 on the input is. And obviously, this is fairly trivial because you just route the bit directly. But the idea is that you can use any values there. You can take all your bits on your input and scramble them to any bit on the output if you want to. So you can do that, and as I said, this is a little CPU. So at the end, if you want to write the data to a peripheral, you also need to actually do that. There's a fair amount of use cases where you don't want to do that, which I'll get into later. And finally, because this is a CPU-like thing, the entire thing is a loop. So you would like to jump back to the start of the program. So. You've seen the example. What specific operations do you have? Well, there's only a few. They fit on one single slide. So you have the set, which, as I said, sets the value of an output bit to some input bits value. Read and write, read data from the DMA stream, and write data from the DMA. Write data to the DMA stream. If you've got your jump, that jumps back to another place in the program. You've also got loop, which uses one of the counter registers, which I'll get into later, in order to loop over a bit of code multiple times. You've got add that can add something to a counter. You've got if that can, jump to a certain location only if a certain bit is set. You've got these two commands which load your counters either from a direct value or from some data read from DMA or somewhere else. And finally, no operation. You also have that. So these operations, you may have noticed that I haven't called them instructions, and that is because they are not. They actually go together in, I'm going to call them an operation bundle. So this is multiple of these things bundled together. You can have up to one read and up to one write. You have up to 32 sets, which means that you can have one set for every single bit in the output register. The output register is 32 bit. And you have one other, so a jump or a loop or one of those add or load control, load counter direct or load counter indirect operations. And this limit is so weird because one operation bundle actually is one instruction. The bit scrambler is a pretty weird architecture that uses instructions that are not 32 bits or not 16 bit. No, instructions are 257 bits wide. We tried 256, but it was one too little, so 257 bits wide. So that's a very long instruction word. And on the flip side, unfortunately, the reason why these are all bundles is that you can execute one of those very large instructions every clock cycle. And given the fact that the DMA subsystem, I think, runs at 200 megahertz, that means that you can shift 32 bits, every single cycle of 200 megahertz. So this thing is very, very fast. So the downside of very long instruction words is that we don't have that much address space. We only have address space for 8 operation bundles for 8 instructions. But given the fact that these things are so powerful, it tends to be enough. Okay, on to the details. I've mentioned counters a few times. We have 2 counters here. They're called A and B. They're both 16-bit. So loop uses them in order to loop over a bit of code, and pseudocode is here. It effectively counts a certain amount. It adds a certain amount to a counter until it is equal or more than the final value. If it is, it falls through. If not, it jumps back in order to loop another time. Pretty standard. And then you have the load counter direct, which just puts a value directly into a counter, and you have the load counter indirect, which loads some sort of value that is read from DMA stream or somewhere else into the counter. Both these can have masks, so they can only set the high or the low value of this, and that can be useful if you want to have 4 8-bit pseudo counters, more or less. You also have add. You can also add a direct value to a counter. And set actually also makes use of the counters. You can have you can address a bit that is offset by a certain counter. So if, say, my counter A is 3 in this example, then my output value would be set to the input bit 4. In this particular case, and that allows you to iterate over the individual bits in a loop, and that can be useful. So readable registers, we already mentioned a few. They're used by sets, they're used by if and if not. And specifically, they are 0 to 63. They're just called 0 to 63. They don't have a name aside from that. These are the bits that are read from DMA. You can access like the last 64 bits. 00 to 031 are the old bits, the ones that are sent to the output the previous cycle. So you can look back at them and use them in order to generate your output bits for the current cycle. That also means that you can recycle them. If you select a bit on your output, a bit on the O register for your output, that means that the next cycle that bit will appear on the O register again. You've got your counter registers, you can also read those, and you have your aux bits. And aux bits have a bunch of comparators in there that compares the A and the B register and the O register in certain ways. It also contains a fixed high and a fixed low bit. So if you want to send that, you also can. Finally, you have the LUT RAM, and there's a little lookup table RAM in the bit scrambler. And what that is, I'll get into later, but just know that you can also select those outputs. So any of those register, any of those bits, you can send to any bit on the output. That is important to know. Okay, so on to the details. As I said, 0 to 63 retains the last 64-bit read from incoming DMA. How that works is the incoming DMA is fed into a 64-bit FIFO, more or less, and the read command actually shifts down the data. So it pops out the oldest data and shifts in a certain amount of new data. So here's a little illustration. If my 64-bit incoming DMA register starts like this, 10, 20, etc., then if I do a read 8, which means read 8-bit, then the entire thing would be shifted up by 1 byte, and the new byte would drop in. So 90 here is pushed in. Same goes for if I do a read 16, but now 2 bytes are put in, and the entire thing is shifted up 16-bit. So the LUT RAM, LUT stands for lookup table. That is what it's used for. So you give it a certain address, and then it'll return the data that is at that address. And that is used for ALU operations. As you might have seen, we don't really have an ALU. You can't do AND or XOR or add or whatever. If you want to, you can use a lookup table in order to do that. You can also do more complicated operations. So for instance, data conversion. If I want to have a picture in linear space, and before I send it out, I want to convert it to have a gamma curve. What I could do is load the gamma curve in my lookup table RAM, and then use the bit scrambler to automatically convert the linear data to one that has a gamma curve on my way to a display of some sort. So the LUT RAM is initialized on startup of the bit scrambler, so you can just dump any data you want in there, and the bit scrambler program can make use of it. And you can use it in 3 configurations. As you see, they all have the same amount of bits, but the ordering is a bit different. You can have 2K bytes, you can have 1K of 16-bit values, and you can have 512 32-bit values in there. This is also selectable on startup. And if you want to figure out how it works in C, it's kind of like this. It uses the most significant bits of the O register in order to look up a value. And LUT out is something that you can select from, so you can send bits from that to your output. Okay, that is more or less the bit scrambler. And I can imagine that you guys are all dazed and confused now, and it's probably a good idea to finish up with a few examples that will also give a little bit more of an idea what you can do with it. So in order to illustrate that, I don't want to just plunk assembly at you. So what I'm going to do is I have an illustration of the data path here. So you have the 5 registers that you can read from on the top. You can select any bit of those and move it to your output. So that is the green lines. And from the output, the red line there's data going back to the O register where it's stored for one cycle, and you can also load the counters from there. Finally, the O and the A and B registers are compared in various ways in the CMP unit, and the O register also works as an input for the lookup table. So first example, we're going to swap bytes. So what you sometimes have is that you have a stream of 16-bit values incoming, but the endianness is wrong. So what you need to do is for each 16-bit value that comes in, you need to swap both bytes. So that's illustrated here. 0123 becomes 2301, etc. So this is peanuts for the bit scrambler. It's a very simple program. Actually, only one instruction bundle. So first, we use the set instruction to set the lowest 8 bit of the output to bits 8 to 15 on the input. We do the same with the highest 8 bits, or actually bit 8 to 15 on the output. We set that to the lowest 8 bits on the input. Then we read 16 bits into the memory register for next time. We write the 16 bit we just assembled, and finally we loop back to the beginning of the program. So in the data path, it looks like this. The lowest 16-bit of the inputs are routed to the lowest 16-bit of the output register, but the bytes are swapped in the middle. So that's it. So we have another thing here. I think I'm missing a slide. I'll just explain. So if you have a display might be very big, like 800 times 600 or something. And the issue is you tend to need to have a frame buffer, which is enough memory to store the RGB value for every single pixel in that display in. So that means that if we go by a very fancy display that does 24-bit color, that means that you need to have 3 bytes for every single pixel. That might be a bit much. So there are tricks in order to minimize that. And one of the tricks is to not store 3 bytes, but to store 1 byte and have every 1 byte be mapped to a certain RGB value that is in a separate bit of memory there. So effectively, you have a palette of 256 colors that you can select out for each pixel. And what those 256 colors are in a different bit of memory. So you can use the bit scrambler in order to do that as well. I'll start with the diagram. So what you would do is you would read your index, your 8-bit value, and you would route that to your output register. And you only do that so it ends up in the O register, because we're going to need that later. In the second instruction, the output from the O register is active, and that is by default sent into the lookup table. And the lookup table contains your RGB values, so it'll look up the RGB value that goes along with that. You can then route that to the output register, and now you have the RGB that goes along with it. So what that looks like in code is this. Again, it's a very simple bit scrambler program. In this case, it's only 2 instruction bundles. So the first bit is, as I said, we route the incoming byte to the topmost byte of the output, because that is where the LUT will be connected to. And we also read the next byte because we have to do that anyway. And then the second thing is we just select bits from the LUT, because the LUT already has done the conversion for us, and then we write it, and that's it. So a final example, this one is a bit more complicated, the 9-bit LCD. You might remember it. So we have 8 bits of data, and we need to prepend each bit of each byte of data with a data or command value. So the way I envision this is you have your bit stream with your values, and then you prepend that with 1 byte that indicates if this is going to be a data or a command. So the way this looks like in the diagram is like this. First, we process that initial byte. So we select that specific byte for the output register, and then we load that into register A, so we can use it later on. So after we've had that first bit, we start processing, and we do that like 32 bits of actually 28 bits at a time. So we read each byte from the input register, and we send it to the output register, but we intersperse it with a DC bit. And the issue is that the output register is only 32 bit, and we occupy 4 bits by the DC thing. So from the last byte that we read, we only can output 4 bits. So in the next cycle, we need to still output those last 4 bits, and then we can also output 3 more bytes, and then we're at an even number again. And if we do this every time, then each clock cycle we will output 7 bytes on the output. Every 2 clock cycles we will output 7 bytes from the input to the output. That's it. So the code for this is a bit more complicated, but it's mostly because of we need a lot of set commands to write the bits in the right order. So we start out by loading bit 0 into the A register and reading 8 more bits. And this is the first half of the actual sending bit. You can see the 4 bits are sent to A0, which contains our DC value. And this is the second half of the moves. At the end, we need to read another 8-bit because we read in a weird amount, so we have to split that into reads, and then we jump back to the loop at the beginning. So I hope that made it all at least a little bit more clear. If not, then please look forward to the TRM as soon as we release that, and I'm sure that there will be a bunch of examples that will end up in ESP IDF as well. So as I said, we hope it comes out in ESP32P4, and this is the end of my presentation. My name was Jeroen Domburg, and this is where you can reach me. Thank you very much for listening.
Welcome to another Q&A session, and for this session we have here Jeroen. So welcome to DevCon and welcome to the Q&A session.
Hi, thank you very much. It's great to be here.
Yeah, so we can go for the first one. So the first question is, will Bit Scrambler be available in other chips besides the announced ESP32P4?
So that's a bit of a funky question to answer, because if the chips are not announced yet, then obviously we can't really give out any details on it yet. What I can tell you is that unless no one actually turns out to use it or need it, the Bit Scrambler is made to be small enough that it can easily be incorporated into other chips as well. So the likelihood is that at least in the larger chips, so for instance the S series, etc., it is very likely that it'll turn up. Again, it's a business decision and it's on unannounced chip, so this is all a bit vague, but that is kind of the direction that you, that we'd expect things to go.
Okay, that's good to know. So we have one more question here, and this question is, would it have the same number of Bit Scrambler FSMs as there are DMA channels available?
So at the moment, not yet. The ESP32P4 has 2 Bit Scramblers, and you can put one of them in a transmit channel and one of them in a receive channel. We're aware that that's likely not very optimal. I would have liked it to be more flexible, but at the moment that is what you get. In future chips, we're likely to make it all a bit more flexible, and if it turns out that you guys all used bit scramblers for everything, then we might also throw a few more in there. At the moment, you get one for a receive channel somewhere and one for a transmission channel somewhere, and that's it.
Okay, I see. So we have, it's not a question, but we have like a quite funny comment here. So the comment is bit planes like Fat Agnos bit processor in Amiga computers.
Well, that's actually pretty on par, because the Fat Agnes back in the day, the idea of bit planes and indexed colors, etc., is all made because the Amiga back in the day had a relatively small amount of memory compared to the resolution of the screens that it could generate. So rather than to just have like a 24-bit frame buffer where each pixel has like 24 full bits of data, they used interesting tricks, like for instance bit planes and index colors, etc. And if you think about it, nowadays embedded controllers like the ESP32 series are not that far off. You obviously have the ability nowadays to, at least in the larger chips, to throw lots of PS RAM at it, with lots still being relatively small, as in 8 megahertz. But if you just want to use an ESP32, putting a full-on frame buffer in there is also pretty challenging. So it's kind of logical to fall back on the same tricks as they used back in the day, and like in index colors is one of those. And one of the things we thought about when designing the bit scrambler was actually, okay, how can we use like 0 CPU power in order to effectively decompress data before it goes to a peripheral, because that saves you lots of memory as well as the CPU power in order to decompress it there. So that's actually a very astute observation. It certainly makes sense.
Sure. So do you have any other consideration or you'd like to add?
I think I saw, while I was talking, a few more questions pop up in the stream. So maybe I can, as it says right there, but a little bit cut off. So you can read the question, I can read the question.
Yeah, so we have one here. Does the read shift in 0 bits are bits at the end of the stream, or how are the DMA edges handled? It looks like the common bundles assume 64 bits have been shifted from the start.
Someone has been paying real good attention here. Thanks. I love seeing technical questions like that, because it means that the whole bunch of technical information I threw at someone at least made one person understand. And that's really great to see that you're all invested enough to actually try to follow the mess of slides that was on the screen. So actually answer the question. So we have a few strategies for that. So the first of all is like a lot of peripherals will have a counter. They will have a counter for a transaction itself. So for instance, if you have, let's see, the parallel IO peripheral that's on the C6, that's also going to be in the P5, I think, that just flat out has a register where you say, okay, the parallel peripheral is going to output n bytes, and after that it'll just abort the DMA transaction all by itself. Or actually, I think it doesn't, but you normally would do that in the software afterwards. So that's one way to handle it. The other way, if a DMA stream is at its end, then you actually do have a few strategies. But it's a little bit complicated, because you don't... So the issue is, say you have a compressed stream, and at the end of the compressed stream, you might still have a bunch of bytes to output. So that makes the entire situation a little bit complicated. And we do have a few strategies for that. And one is to effectively say, okay, if the input stream is at its end, then you should allow at most n bytes to be written to the output stream, because we know that the bit scrambler will continue running for a little bit and then it'll end. The other thing is that say you have a program that reads a byte and then outputs a certain amount of bytes and then reads the next byte, then you can also say that, okay, if the input stream is at its end, then it's allowed to read at most X more bytes before we abort the bit scrambler program and call it a day. So those are the strategies we have right now, and they will, it'll probably be sufficient for 99% of the use cases. As I said, just because the nature of the beast, there's no real great solution for that. You run into the halting problem and other issues. So.
Yeah, okay, so thank you. So I think we have no more questions from the audience. We'll be still like available to answer questions by the chat. So I'd like to thank you for being part of this Q&A and answering all the questions.
Yeah, you're very welcome, and to everyone who's watching, like, thank you so much for being interested.
Yeah, it was a really interesting talk. So, and now we can go back to the studio.
Bye-bye.
Great presentation by Jeroen, and some interesting questions afterwards. Didn't expect any less from Jeroen, to be honest. So this was the 5th talk in a row, and I think we need a short break right now. So how about 15 minutes? Sounds good?
Sounds good to me, yes, absolutely. We don't want our viewers to feel overwhelmed with tons of information. So yeah, let's take a short break and get back online in 15 minutes for the second session of the day, which comprises another 4 really interesting presentations. See you in a bit. Hi everyone, you're watching the live streaming of DevCon23 by Espressif. We are
Ivan
and Yanis, your hosts for today, and this is the second session of DevCon23, which includes 4 presentations in total. The first one is entitled Low Power Features of ESP32 CEST, Target Wake Time and LP Core. It will be delivered by Marius Vikhammer, who's a tech lead in our Shanghai office, and by Sudeep Mohanty, who is a senior software engineer in our Brno office. So despite being in different countries, the guys have made this presentation together, which is only a small example of a strong collaborative culture across different branches at Espressif.
Marius and Sudeep will highlight some of the low power features of ESP32 CEST, which is our first triple protocol microcontroller with Wi-Fi 6, BLE5 and 802.15.4. In their presentation, they will show the features related to the low power core and also the target wake time and how they can be used together to achieve quite feature complete but power conscious products.
Hello and welcome to our talk. With great power comes shorter battery life. Today we are going to talk about power consumption on ESP devices. Specifically, we'll focus on the ESP32 C6. I am Sudeep Mohanty and I'm joined by my colleague Marius Vikhammer. We are part of Espressif's IDF core team and we work on ESP IDF, which is Espressif's IoT development SDK. We work on a lot of things like low power coprocessor, FreeRTOS, memory, panic handlers, and a lot of other things. And today we are going to go into the various sleep modes and low power coprocessor that we have. Just touching on the different topics that we are going to talk about today. First of all, let's look at why we should care about power. Then we will take a look at the different power management methods that we have in ESP IDF. And then we will focus a bit on the different new features that have been added to ESP32 C6. Now I'll hand it over to my colleague Marius to take us further.
Thank you, Sudeep. So why do we even care about power consumption? We have our ESP32 dev kit, right? And we just plug it into the USB and we have power. Doesn't really matter, right? Well, in some cases it does. Power consumption equals to heat, which might impact your design of your embedded system. There's also the environmental impact of using all of this power. And most importantly, you might want to run your device off a battery. And the larger the power consumption is, the shorter your battery life is. And this is where it really matters. So first we'll talk a little bit about the power management in ESP IDF that we provide for you guys. So in general, how do you decrease power consumption on a microcontroller? There's a few generic methods. You can power down certain areas of the chip. You can do what we call clock gating, where you turn off the dynamic clock for a certain peripheral or the whole chip actually. Or you can decrease the voltage and or the frequency of the chip. In ESP IDF, we provide this through our 2 libraries. One is power management. We call it ESP PM. And the other one is ESP sleep. First, we'll go through a bit about our sleep modes. What you have and what you're most familiar with is the active mode, where basically everything is powered up and everything is running at full speed. In this mode, all the functionality is available, and you might have a power consumption up to 350 milliampere, depending on your Wi-Fi activity. The next one is modem sleep. And in this mode, basically the RF part of the chip is powered off while everything else stays on. And then we have light sleep. In light sleep, the RF part is also powered off. But in addition, you can also power off your digital peripherals. Which digital peripheral is powered off will depend on your chip. On some chips, you can power off a lot of them. On some chips, There's a more limited selection. In addition to this, your CPU is also paused. But in light sleep, when you wake up, you can just continue from where you left off. Since the memory and all of the states are still intact, there's no actually a need for a long wake-up procedure there. You can just continue your software where you left off. In light sleep, you're looking at power consumption from 35 microampere and upwards. And these numbers are from the C6. Next, we have deep sleep, which is the most commonly used sleep mode on our chips. In deep sleep, we just basically power off everything we can power off. The main CPU is off, the main internal memory is off, RF is off, and all of the digital peripherals are off. The only thing that must stay powered on in deep sleep is the RTC part and the power management part, as well as the RTC memory, which is a small bit of memory that stays powered on even during deep sleep. And then there's two optional parts. On some of our chips, we have something called the low power CPU or the ULP. This is like a small extra processor that can do some simple tasks while the rest of the chip is sleeping. And this low power CPU can access the outside world by using the RTC peripherals, which are some limited peripherals that may stay active during sleep. For example, on C6, there is a RTC I2C bus that lets the low power CPU use I2C even while the main CPU is in deep sleep. The main drawback of this mode is that since both the CPU and the internal memory is off, there is no states saved. So basically, when you wake up from deep sleep, you start all over again. Your app restarts bootloader. But it gives you the lowest power consumption, as low as 7 microampere if nothing is powered on. Okay, we have talked about sleep modes, but how do you actually wake up from them? Well, we have what we call wake-up sources, which you configure before sleeping, and you can have multiple sources. Not all of the sources will work from deep sleep, and like exactly which sources you have will depend on your chip. This is something you have to look up in the TRM. So just to summarize, with light sleep, your state is retained during sleep, and you can quickly resume from where you left off before sleeping. But since we're not powering down everything, the power consumption is not as low as you could have it. Whereas with deep sleep, you get the lowest possible power consumption, but everything is wiped except RTC memory. And since you're booting from scratch again, it might be very slow to wake up. And then when you wake up, if you actually want to do something, you have to initialize everything again. So from this, you can see that sleep modes are a trade-off. It will depend on your application which one is the best. And then in IDF, we also have ESP PM, our power management library. And it provides two basic features. It's automatic light sleep and dynamic frequency scaling. With automatic light sleep, we base it on something called FreeRTOS tick idle, which basically means that instead of your idle task just staying idle for a few seconds or a few milliseconds, it will basically stay idle until there's something else to do. So what happens there is that FreeRTOS is executing tasks, and whenever it goes to idle, then it will try to calculate when is the next time I actually have to do something. And if that time is a certain amount of time from the present, it will say like, okay, I can put the chip to sleep. And then we'll stay into light sleep all the way until it actually needs to do something. And this way, light sleep is just handled automatically for you from IDF. All you need to do is just call the PM init function. It's very simple and very inconvenient. Here you can see a little bit what's actually happening with the power consumption during such an auto light sleep. In this case, we're running basically Hello World that prints Hello World every 1 second. What you see first there is the boot up process before it goes into light sleep for a while. And then it wakes up for a short period of time and prints Hello World before going back to light sleep again for 1 second. So with automatic light sleep, it knows that nothing will happen before 1 second in the future when I need to print Hello World again. I need to wake up. And this way you can save a lot of power. If you look at the next plot here, you can see actually how much power it is during light sleep here. It's hovering at around 50 microamp. before shooting up when waking up to do light sleep. Print hello world. And then we have dynamic frequency scaling, which lets ESP IDF basically automatically adjust your APB and CPU frequency and therefore save power. And the whole system is based around power management locks, which lets application just take a lock, which expresses their requirements for the CPU frequency. Let's say a certain peripheral needs the CPU frequency to be at max speed while working. You can just take this lock. As soon as it's finished, it will release the lock, and the system knows, okay, now I can scale down the frequency. This was just a short introduction to our different power management methods. You can find much more information online. There's a bunch of API guides linked on the left side there, as well as 5 different examples showing different power-saving mechanisms. And then now on to what we actually want to talk about, our new chip, the ESP32C6, and how we have improved it for lower power improvements. So basically, on the C6, we support Wi-Fi 6, which has what we call target wake time. And why this is important, we'll get back to later in this discussion. There's also a new and improved ULP, a low-power coprocessor, as well as a more flexible power management unit, the PMU. And now we come to the exciting new feature on the C6, the target wake time. And for this, I'll let Sudeep handle the talk. Over to you, Sudeep.
Thanks, Marius. So Wi-Fi target wake time. Before we get into target wake time and what it is, let's look at a story of IoT and Wi-Fi. If you look at some market predictions, what you see is that IoT market is growing and growing fast, exponentially. Another thing that you will notice is that a lot of devices which are IoT devices are actually connected by Wi-Fi, probably a third of them. This is because Wi-Fi is very widely used, and IoT devices are deployed in a lot of places where Wi-Fi is already present. So it is quite natural to have a lot of IoT devices, connected devices, which rely on Wi-Fi for connectivity. But unfortunately, Wi-Fi is not known to be very power efficient. Now let's look at what problems that we have with Wi-Fi and how the existing Wi-Fi power save techniques work for IoT devices nowadays. If you know how a Wi-Fi system works, what you will notice is that there is an AP which sends out broadcast beacons to all its connected stations with a beacon interval. And all the connected stations need to reply to this AP for the data transmission to happen, to work. Now, traditional Wi-Fi power save techniques rely on these beacons and the time between each beacon. This is the time, essentially, which is called the beacon interval, which a station can use to sleep or to conserve power. But every now and then, the station will have to wake up at every beacon interval and reply to a beacon that is sent by an AP. In some cases, some stations could take a bit more advantage and not reply to all of the beacons that are sent by the AP, but probably reply to every other beacon or every third beacon. And this also can help in saving some power. But these beacon intervals is in milliseconds, so the amount of sleep that a station can do is quite low. So it may not be very effective in conserving power. The other problem that has come up with a proliferation of IoT devices is that there is increased contention of the Wi-Fi network. What that means is, since there are many devices now in the same network, they use the same medium to talk or to communicate, and occasionally there could be collisions. And if there are collisions or packet losses, then a device would need to retransmit the packet. Now, every time a device has to retransmit a packet, that would mean an increase in power consumption. Also, it in a way reduces the efficiency of the network. So these are the problems that we see with Wi-Fi being deployed on IoT. And up until now, there were no great techniques to conserve power when you're connected to Wi-Fi using on an IoT device. But recently, Wi-Fi Alliance has come up with Wi-Fi 6 standards. The Wi-Fi 6, or in other words, 802.11ax standard, has something called as target wake time. And this feature promises to tackle both of these aforementioned problems. Let's take a look at how target wake time does this. So what we talked about earlier is that a Wi-Fi AP sends out beacons periodically, and the station needs to reply to these beacons. The target wake time allows the station and the AP to negotiate a schedule of sleeping and waking up, and thereby can have its own sleep duration, which is irrespective of when the beacon interval is. So for example, if a station is connected to a Wi-Fi 6 AP, which has target wake time enabled, the station can negotiate its sleep time and can go to sleep. In the meantime, if the AP sends out some beacons, the station is not obligated to reply to these beacons, and the connectivity between the station and the AP will still be maintained. Now, once the station wakes up, the AP, since it knows when the station is going to wake up, will buffer any data that is meant for the station and will just transmit it once the station wakes up. So this way, what you see is that the AP and the station do not lose connectivity when the station wakes up and can receive packets. Since the negotiation happens between the station and the AP, and the station can then negotiate for an interval, which is called the TWT interval, it could be much longer than just beacon intervals, which are in milliseconds. TWT intervals could typically be in seconds, minutes, hours, or even days. And this bodes very well for IoT devices, which use Wi-Fi infrequently and could have a long sleep duration. Now, the second problem that we had talked about was overcrowding of the network. Now, how does TWT help solve that? Now, imagine you have a Wi-Fi 6 infrastructure which has two devices which employ target wake time. Now, both devices can negotiate their own sleep schedule, and they can have their own sleep and wake durations. What this does is that it staggers the sleep and wake schedule of both the stations, and thereby it can reduce congestion of the network because both the stations are using the network at different times. So in effect, this would increase the network efficiency, as well as it could result in lesser collisions and lesser packet loss, and therefore the stations don't need to retransmit data, which means much less power consumption. So to summarize what we just saw, target wake time is a feature of Wi-Fi 6 or 802.11ax standard. Target wake time allows a station or a device and an access point or a Wi-Fi router to negotiate something called as a service period. Now, the service period essentially determines when and how frequently will the station and the AP exchange data on the network. And in effect, this allows the station to sleep for a longer period of time and can save much more power. There are two types of target wake time. One is called individual TWT or ITWT. Here, each station is responsible to negotiate its own sleep schedule. This is already supported on ESP32C6 from IDF 5.1 onwards. And you can see an example already. If you want to know how, if you want to fire it up and try it for yourself, the example is in ESP IDF. The second kind of TWT is called broadcast TWT. This is meant for the AP, where the AP sends out TWT parameters to a group of stations in multicast or broadcast fashion. So the AP controls when the stations would wake up and exchange data. This is not yet supported on ESP32C6, but it shall be supported soon. Of course, as you might have figured out already, that to take advantage of TWT, what you need is a Wi-Fi 6 infrastructure with target wake time enabled. So if your device is being deployed in an infrastructure which is compliant to Wi-Fi 6 and has target wake time, you should be able to take advantage of target wake time. Now, we had touched upon the different sleep modes that we employ on ESP devices, and one of the most popular one is deep sleep. We can shut off almost everything, including the RF modules. That means that there is no Wi-Fi connection during sleep time. Although you can save a lot of power, but maybe you will not be connected to Wi-Fi when you are sleeping. Now, in this experiment, we present target wake time combined with automatic light sleep and dynamic frequency scaling as an alternative to deep sleep. The advantage here is that the Wi-Fi connection is maintained even during sleep. Now, how does that work? Well, the Wi-Fi AP buffers the packets for the station during sleep. And once the station wakes up, then the Wi-Fi AP will transmit those packets which have been buffered for the station. Now, this means what you can potentially do is that you can build products which are more responsive to network events, as opposed to employing deep sleep, where you might need to reconnect to Wi-Fi once you wake up from sleep. Now let's take a look at this and how it responds, or how it reflects in the power graphs or power curves when we are comparing target wake time with deep sleep. To do this experiment, what we need is a current consumption measuring device, such as a joule scope connected in series with an Espressif chip. Then we can measure the current consumed during different phases of your application. Okay, the first graph that we have here is for deep sleep, when, let's say, the sleep interval is about 15 seconds. So what you can see here is that typically the device boots up, it connects to Wi-Fi, and then goes to sleep for about 15 seconds. After 15 seconds, the device wakes up again. It has to reinitialize everything. It has to reinitialize Wi-Fi as well, and it has to reconnect Wi-Fi, and so on and so forth. This is how a typical application would look like, which employs deep sleep as a power consumption method. Now, how does this graph change if instead of deep sleep, we use target wake time with the same TWT interval of about 15 seconds? What you see here is slightly different curves. Well, of course, the ESP initializes and it connects to Wi-Fi. And then it negotiates with the AP about a sleep schedule. So this is where the TWT negotiation takes place. And once that is done, and once a service period is agreed upon, the station now goes into sleep. Now, in this example, or in this experiment, what we do here is that we allow automatic light sleep and dynamic frequency scaling to take effect once we go into sleep. So the power consumption reduces, and every 15 seconds, for example, the station device wakes up and sends out a TWT probe to the AP. And this is how the TWT protocol works. Now let's zoom into these graphs a little bit more. If you take a look at the deep sleep graph and we zoom into it, what you will notice is that the steady state sleep current is about 7 microamperes, which is quite low. But if you do the same on a target wake time on TWT, you see the sleep state current is about 35 microamperes, which is significantly higher than deep sleep. Then if you look at just this data, you might think that deep sleep could be more effective than target wake time. But that's not the case. That is because what you will notice is that during deep sleep, what you need is you need to boot the ESP again. Then you need to initialize the Wi-Fi, and you need to reconnect. And this takes about 12 seconds in our experiment. And this consumes more energy. As compared to this, when you employ target wake time, you see that the minimum active time, or the time it takes for the device to wake up and send out the TWT probe and do whatever it needs to, is about just 200 milliseconds. Now, this results in an average current consumption, which is far lesser. You can see if we have a 15-second interval with deep sleep, it consumes about 16 milliamps. But if it's target wake time with a similar 15-second interval, it consumes about 9 milliamp amperes. So you see, the current consumption could be way less when you employ TWT. But that doesn't give you the full picture. What you need to do is to analyze this a little bit more depending on your application. Now, as we had talked about, IoT applications could be such that the sleep durations could be way longer. Now, we did an experiment where the amount of sleep or the time that you need to sleep varies, and we wanted to see what is the power consumption of deep sleep versus target wake time. What we noticed here is that when the sleep intervals are less, maybe a few seconds, 10 seconds, maybe 15 seconds, target wake time performs much better than deep sleep, simply because a lot of energy is wasted in booting up the ESP again and reconnecting to Wi-Fi. So this is the difference that you see when the wake-up schedule is very fast. But what you notice is that once your wake-up time or your sleep duration increases, the difference between target wake time and deep sleep minimizes or reduces. Let's say at about 10 or 15 minutes, it's almost the same. At about 30 minutes sleep duration, you might find, or at least in our experiment, the deep sleep current is slightly lower than the target wake time current. So what you see here is that for your application that you're building, you will need to do some kind of power curve analysis like we have done here to understand which sleep mode suits your applications the most and what is the optimum power consumption that you can achieve with different sleep modes at various scenarios of where your application is. So just to summarize, what we learned so far is that deep sleep is one of the most popular ways of saving power on ESPs, but there is no Wi-Fi connection during sleep. Now that we can overcome that by using target wake time and automatic light sleep and DFS. There is Wi-Fi connection which is maintained during sleep. The Wi-Fi AP buffers packets for the device, so we have potentially more responsive networks. But of course, like we also saw, no sleep mode is no single sleep mode is good for all kinds of solutions. You will need to do some kind of an experiment like the one above to understand which sleep mode suits your application the most. Moving on. The next topic that we want to talk about is the low power CPU, or the ULP code that we have on the ESP32C6. What you will notice on your right is the functional system diagram of ESP32C6, and in this you will see the LP RISC-V coprocessor. This is a 32-bit RISC-V processor and supports RISC-V IMAC instruction set. And the whole purpose of this low power core is to complement the high performance core, and this low power core can run during deep sleep. So if you want to do some meaningful actions like reading some sensors or talking to external data or moving some actuators, even while you're in sleep mode, you can do that with the low power RISC-V core. A little bit of specifications of the RISC-V, low power RISC-V core. It operates on 20 megahertz clock. It has a two-stage pipeline, 19 vector interrupts. It has access to 16 kb of low power SRAM, and it also has access to many low power peripherals, such as low power UART, low power I2C. So typically, if you are in deep sleep and you would like to use or you would like to interact with the external world on your device, a low power core can help you with that. Of course, the low power core can wake up the high performance core using an interrupt and can wake it up from sleep. And when you are in active mode, then the low power core also has access to all of the different system peripherals and the system memories. So in effect, the low power core could act as another core, a second core on ESP32C6. If you want to get into the details of how ULP works and how a program is compiled for the ULP or the low power core and how it runs, then you can look at the various references that we have. So we have some detailed documentation about ULP core here. We have a bunch of examples also about the low power core, so you can try them out. We also have a dedicated YouTube talk from last DevCon, which is DevCon 2022. And you can also watch this and get into the details about how the low power core works. So with that, we will now move on to the final power management unit, which is new in the ESP32C6. And I would like to hand over the baton to Marius to talk us through it and bring us to the end. Marius.
Thank you, Sudeep. The power management unit is something else we also improved on the C6. If you see in this next slide there's a comparison between the different peripheral and power domains in C3 on the left and then C6 on the right. And if you look at the ones with the green color, it's the one that will stay powered on during light sleep. But there's also a small cog in some of them, which signifies that they can be powered off during light sleep. And if you look here, the PMU on the C6 has a lot more peripherals it's able to power off. It can basically be configured to power off everything if it wants to. It's much more configurable. And this results in a much better light sleep current on C6 compared to our previous chips. As a comparison with C3, on C3 you could get around 130 microamps as a light sleep current. While on C6 you can get it all the way down to 34. So it's almost a reduction of 75% in light sleep, which is pretty. And then just to give a conclusion of our whole talk, optimizing for power consumption has become very important, especially for battery-powered devices. And with the ESP32C6, Espressif is putting more focus on this low-power part of the chip. And with the C6, we provide a granular control of power domains with our new and improved PMU. We have Wi-Fi 6 features such as target wake time to further optimize power consumption for Wi-Fi connected devices, as well as an improved low-power CPU with capabilities to perform tasks even during light sleep. Even during deep sleep. Yeah, that was what we had for you guys today, and I hope you guys enjoyed the talk. Any questions?
Welcome to another Q&A session. And now to answer your questions, we have here Marius and Sudeep. Hello, guys. How are you today?
I'm good. Hi, Pedro. Thanks.
Yeah. So thank you for being part of Espressif DevCon23. We are pretty happy to have you guys here. So I think we can go for the first question. So first question is, will the ESP32 C6 TY still use the full PM block from initialization or to de-initialization?
Regarding that TWI driver, I'm not that familiar with it, but we can make a follow-up ticket for it and check that if it's really necessary anymore, or if we can improve that.
Okay, thank you. Yeah, so we will try to answer some of the questions by the chat. So some questions we need to check with other teams. So be patient. We will try to answer all the questions. So now continue to the second question. Can you combine deep sleep with Wi-Fi target wake time?
Thanks for the question, Pedro. When we have deep sleep enabled, we try to conserve maximum amount of power, which basically means that we turn off our RF modules, or essentially we turn off our Wi-Fi and also most of the memory. So basically we lose all information to connect to a Wi-Fi network. This doesn't work with target wake time. Because what target wake time protocol dictates is that we have a method to quickly connect to a Wi-Fi AP and then go back to sleep. So to answer your question, unfortunately, we cannot combine deep sleep with target wake time. However, in this presentation, what we present is that target wake time can be an alternative to deep sleep. And we urge all viewers or users of ESP32C6 to conduct experiments based on which power safe method is better for their application.
Okay, so I see. Thank you. So we have another question here. So the question is, which Espressif modules have support for DVFS? So Marius, we are not able to hear you.
I could probably take that question then. Well, DVFS, or in Espressif's ESP IDF terminology, it's DFS, dynamic frequency scaling. This is supported via ESP IDF on ESP32 and later as well. The documentation about this would be available under the power management chapter in the API references.
Okay, I see. Thank you. So we have one last question here. So the question is, are some of these features available on the ESP32S3?
Yes, so dynamic frequency scaling is definitely available. All the sleep modes are also available on ESP32 S3 as well, except for target wake time, which is a Wi-Fi 6 specific feature. So that's available from ESP32 C6 onwards.
Okay, thank you so much. So we had a little issue with Mario's audio, but it's okay. So I'd like to thank you guys, not only for the talk, but as well for answering the questions and being part of this year's DevCon. And we will be happy to answer any other questions by the chat.
Okay, thanks, Pedro.
Yeah. Now we can go back to the studio.
Our next presentation will be delivered by Hrishikesh Dayagude, a Senior Engineering Manager in Pune, where Espressif's Indian branch is located, in collaboration with Piyush Shah, a Senior Product Manager who is also based in Pune. Their talk is entitled A Matter Ecosystem with ESP Rainmaker. Matter is an industry unifying protocol built by the Connectivity Standards Alliance. Basically, Matter is a protocol that connects compatible devices and systems with one another, even if they are provided by different brands. Smart home devices should be secure, reliable, and seamlessly connected, and with Matter, they are.
In fact, Matter is a local network protocol, so other aspects of device management such as user management, access control, and so on have to be dealt with by developers. ESP Rainmaker, which is Espressif's end-to-end cloud solution for IoT devices, offers a private Matter ecosystem. Hrishikesh and Piyush will explain the various concepts related to such an ecosystem, and in particular they will focus on a device type called Matter Controller. So let's listen to what Hrishikesh and Piyush have to say.
Hello everyone, welcome to the Espressif Developer Conference 2023. The topic for this session is Matter Ecosystem with ESP Rainmaker. It will be presented by me, Piyush Shah, and my colleague Hrishikesh Dhaigude. So let me first give my own introduction first. So I have over 15 plus years of experience working in the field of Internet of Things, which is known as IoT. I have been part of various product teams right from the very early stages of IoT. I worked with a large number of customers and have a deep understanding of typical customer requirements and ways to address them. I have extensively worked on different IoT SDKs and Apple HomeKit being one of the key products. So considering all of this experience, now I have transitioned to a role of a product manager. And I'm currently managing various products at Espressif like the HomeKit, ESP Rainmaker, and ESP Insights. So this is roughly the flow of the session. We'll first talk about Matter, then we'll see what a Matter ecosystem is. Then we'll talk in brief about ESP Rainmaker, then the combination of Rainmaker plus Matter, and then my colleague Hrishikesh will go over the details of Matter Controller. So what is Matter? So Matter, which was previously known as Project Chip, is the new foundation for connected things. It is guided by the Connectivity Standards Alliance, which is also called as CSA, and it is developed through collaboration amongst all the leaders of the IoT industry. So all the companies that are typically involved in IoT and IoT ecosystems, like say Apple, Google, Amazon, and other appliance manufacturers, solution providers, all of these are part of this alliance. A Matter focuses on building connected devices that are secure, reliable, and importantly, seamless to use. The Matter specifications are meant for secure interaction between IoT devices in the local network, ensuring interoperability. So this interoperability is a key point because today, if someone wants to have control via HomeKit as well as Google Voice Assistant or Alexa, they have to do configuration from various different apps to link their account with these ecosystem accounts and then use the ecosystem of their choice. So it is a bit painful for the end users, but it is even more cumbersome for the manufacturer because they have to add the support for all of these ecosystems. And then the efforts and time to market increases. And there are also several certification costs involved. So Matter simplifies all of this because now you have a single specification which works with all of the ecosystems. And not only that, different devices from different vendors can also work with each other, which makes interoperability much more better to use. So let's talk about Matter ecosystem. So in the earlier slide, we mentioned that Matter is a local network protocol. Specification to be precise, because it is not just a single protocol, but a combination of different protocols. So one local network can have multiple logical Matter networks, which are called as fabrics. All nodes in a fabric can identify and communicate with each other securely. And a Matter node can be part of multiple fabrics. So Matter ecosystem is the entity which creates and manages such fabrics. So if you look at the diagram, there you can see that there are two different fabrics. One is in the green color and one is in the red color. So fabric is actually a local network entity. And as I said, the combination of various such fabrics is an ecosystem. So we may use the term fabric and ecosystem interchangeably. So here red is one ecosystem and green is one ecosystem. So the phone, the smart wall switch, and the light are part of the green ecosystem, which means that they can talk to each other. And the same light is also part of the red ecosystem, and it can communicate with the voice assistant separately. So typically you can consider this an ecosystem as something like HomeKit or Alexa or GVA. These are the standard ecosystems that we are aware of today. So let's talk about Matter identities, because that is the main piece of the Matter ecosystem. So Matter uses PKI to facilitate identity. PKI means public key infrastructure. So each node in a Matter fabric has a certificate called as a node operational certificate, which is also called as NOC in short, that is used to identify a node on the network. All these nodes in a fabric share a common root of trust, that is a root CA, to validate each other's NOC. So basically the root CA defines a fabric, and using the root CA, the certificates are signed, which are called as NOCs. So when a Matter node is part of multiple ecosystems, it has multiple of these NOCs, one for each ecosystem it supports. So here you can see we have shown the NOCs for the different devices. So the phone and smart wall switch each has one NOC. The voice assistant has one NOC, but the light bulb has two NOCs because it is part of two ecosystems. So what are the key components of a Matter ecosystem? So first and foremost, we said that it's the PKI infrastructure management, which is basically the root CAs and NOCs. Then user management, because the Matter specification defines the communication on the local network, but it does not say how you manage the users and their interaction with their devices. Access control mechanism is also important point. So again, here the Matter specification has a mechanism of access control, but all of that is limited to the local area network. There is no link to the real life entities like users, phones, and other such devices. So Matter ecosystem also requires an interface for commissioning, control, and device binding. So commissioning basically means onboarding a Matter node onto your Wi-Fi network. And bindings means creating automation such that an event on one Matter node triggers some action on some other Matter node. So the interface here typically means a phone app. You must have seen Apple Home app or Google Home app or Alexa app. These are some examples of interfaces for Matter ecosystem. Then there is data storage for Matter nodes. So when the phone and the devices are in the same network, the phone can obviously discover the devices on the local network using MDNS. But if the phone is not in the network, it still needs to show the user what all nodes are linked to that user's account and what controls are available for those nodes. So for that, some data storage in the cloud is required. And the last point is remote control. So again, to repeat, Matter specification talks about communication only on the local network, but most cases require you to control your devices from some remote location. So that is one key component of a Matter ecosystem. Now let's talk about what is ESP Rainmaker. So I'm sure a lot of you must have already heard about it, but let's just go over it in brief. So Rainmaker was launched in early 2020. It is Espressif's end-to-end platform for IoT products. It includes a cloud backend, phone apps, firmware agent, voice assistant integrations like Alexa and GBA, and a device management dashboard. So Rainmaker is a typical IoT cloud app which offers all the standard functionality like user management, node access control, remote and local operations, scheduling, grouping, sharing, scenes, OTA firmware upgrades, status monitoring, etc. So basically it has all the pieces that are required for any IoT ecosystem. So now let's talk about ESP Rainmaker as a Matter ecosystem. So as I mentioned, like ESP Rainmaker already has all the components that are required for any IoT ecosystem. So we extended the concepts in Rainmaker to support Matter. So the first point is the PKI infrastructure. So as I had mentioned earlier as well, this is the most important aspect of a Matter ecosystem. So Rainmaker already had a concept of groups. So to support Matter, we have sort of reused the groups as matter fabrics. So each group has its own root CA and then associated NOCs. So the root CA can sign two types of NOCs. One is the commissioner and controller nodes, and others are end nodes. So commissioner and controller nodes are typically your phone apps or controllers like a wall panel or a voice assistant. And end nodes are your devices like light bulbs, outlets, blinds, air conditioner, and other such devices. The next is user management. Again, to repeat, matter specification just treats all the entities as nodes. But in real life use cases, the user management concept comes into picture because the devices need to be linked to some user. So each user in Rainmaker gets an NOC which is linked to the group. So basically all the users which have access to the groups get their own NOCs to commission and control the matter devices. Access control. So a matter device which is commissioned into a group gets an end device in NOC, which allows it to interact with other nodes under the same group. So the interaction here could be via bindings or the normal control from the phone app or the controller. Then a user interface. So the ESP Rainmaker phone apps have been extended to support matter features. So we have ensured that the overall user workflow is same as it was earlier, but still supports matter functionality. So Rainmaker had soft API and BLE based provisioning. In the same workflow, we have added matter commissioning, which is basically onboarding of devices on Wi-Fi. Then there is local discovery using MDNS and then control over secure matter sessions. And then there is support for binding. So Rainmaker had cloud-based automations. For matter, now we have local bindings. Just to repeat, it is basically means that some event on one matter node can trigger some action on some other matter node. That is what binding means. And then the last point is matter controller. So Rainmaker Fabric has enabled a special device category called controller, which is a combination of Rainmaker and matter features. So the controller has MQTT credentials like any other Rainmaker node, and it also has matter NOCs. Additionally, it has some permissions specific to the user so that it can fetch the list of all matter nodes from the cloud directly and then show it on its interface. So what are the benefits of matter ecosystem or the Rainmaker as a matter ecosystem? So typically you already have options like the Apple, Google, and Alexa ecosystems. But still, there are some things that require a custom ecosystem. So the first point is better control on the user experience. Like if you own the matter ecosystem, you can have much more control on how the interface for the ecosystem is and what features you provide. Like there could be some custom functions which are not part of the standard matter specifications, but still you want them on your end devices. You can enable it via your own app and ecosystem. So it can also allow onboarding other matter devices onto the fabric. So for example, you are a company making lights and you want to integrate with sensors which are made by some other company. You can onboard those sensors onto your matter fabric or say switches from some other vendor onto your fabric, and they can be used to control your lights. So the next important advantage of Rainmaker is that it is a hubless ecosystem. So all these standard ecosystems today require a hub, which is typically a speaker or something like an Apple TV. But with the Rainmaker ecosystem, don't need any hub. So it allows a much wider market reach because in a lot of developing markets, the consumers won't have hubs at their home, but they would still have phones. And Rainmaker enables matter even for such users. So it again allows implementing special device types like controllers, which I mentioned that it is a combination of Rainmaker plus matter with some additional user level privileges. Then Rainmaker can be deployed in any AWS account. So it also means that this matter ecosystem based on Rainmaker can also be deployed in any AWS account. So it basically gives you a private white label matter ecosystem. And the last point is it enables remote control. So if there are matter-only devices in your network and there is a controller which is connected to the internet, you can also control the other Matter devices via the controller. So now we'll see a demo of how our phone app onboards a Matter node and does some basic operations specific to a Matter fabric.
Hello everyone. In this part of the session, we'll talk about the Matter controller. Before jumping into the details, I'll give you a brief introduction about myself. My name is Rishikesh Dhaigude and I work as a senior engineering manager with Espressif. I have around 12 plus years of experience working in the IoT domain. I have been involved since the early days of Matter for around 3 years now. I am primarily responsible for Espressif's contributions in Connectivity Standards Alliance for Matter. I am an active contributor in the Matter open source repository, which is the Connected Home IP. I am responsible for managing the Espressif's SDK for Matter. ESP Matter is built on top of Connected Home IP and provides a simplified set of APIs, a few production references, and tools and scripts for manufacturing, security, and production. Now, let us go into the details of the controller. As Piyush mentioned, Matter controller is a special category of Matter node which can discover and control other Matter nodes in the fabric. Imagine this to be like a wall panel with touch controls or a speaker or a gateway kind of device. In case of wall panel, you will be able to control your devices using the UI, whereas in case of speakers, you can use your voice commands to control different devices. In this case, a Matter control is both a rainmaker as well as a Matter node. It means that the controller has the functionality of both rainmaker as well as Matter. Additionally, it has access rights similar to that of the user's phone. Now, let us go into the scope of the controller. the first and the foremost thing is that a controller should allow commissioning of Matter nodes. For example, if you get a new Matter device into your home, a controller that is mounted on one of the walls in your rooms should be able to commission or set up the Matter device. The next thing, it should be able to discover and control nodes in the local network under the same fabric. Now, Matter is a local network protocol, which means that the Matter specifications do not talk anything about remote connectivity. But remote control is extremely important for seamless operations of the devices. This controller can provide remote control access for the Matter nodes. Matter provides device-to-device automations. It is a very useful feature wherein two Matter devices can communicate with each other without having to go through a cloud or a third-party entity. This is possible through a feature called as binding. Controller can allow to create these bindings. Next part is the OTA. Again, as Matter is a local network protocol, not all the Matter nodes will be connected to the internet. Matter facilitates OTA through distributed compliance ledger, which is like a secure and distributed database that has all the information related to the OTA for a particular Matter device. The controller can fetch the OTA from the DCL and then pass it on to the Matter node so that it can perform the OTA. The last thing is the controller can manage access control for various users under the same fabric. For example, there could be different kinds of users, like an admin user, non-admin user. An admin user is someone who can control everything, anything and everything in the fabric, whereas a non-admin user is someone who has limited functionality control. Now, let us go into the controller workflow. As you can see in the diagram, the user first commissions a light bulb or a Matter end device into the Rainmaker fabric. The next thing is it commissions the controller into the Rainmaker fabric. This is followed by the user node association between the phone and the controller through the cloud. Next is the controller configuration is installed on the controller. Both of these operations happen through the custom clusters that are present on the controller. Once the controller is validated, it gets the NOC and the commission devices list from the cloud. Then it performs discovery on the local network. Once the discovery is complete, it can then control the devices present locally using Matter. Now let us see how the local remote control happens. In case of remote control, the user is not present in the home network. So the user from outside issues a command to toggle a bulb, for example. In this case, the command reaches the cloud and the cloud sends it to the controller over Rainmaker. The controller can then perform the actual action like toggling the bulb using Matter on the local network, of course. Now, let us take a look at the Matter controller demo.
In this demo video, we will showcase adding a Matter controller into the ESP Rainmaker fabric so that it is able to control other Matter accessories like a light and an outlet in the same fabric. First, we will commission a light bulb into the Rainmaker fabric using the Rainmaker phone app. Now you can see that the light bulb is commissioned. The phone app shows the light bulb along with a Matter switch that has already been commissioned into the fabric. You can now control the light bulb features through the phone app, like the brightness, hue, turning on and off the state, and so on. Next, we'll commission the Matter controller, the ESP32 S3 box at the center, into the Rainmaker fabric. Once the commissioning is complete, we will link the user account with the controller so that the controller can perform any operations on behalf of the user. You can see that the light and the switch are seen on the UI and can be controlled. Here we are controlling the light. Finally, we'll commission an outlet present on the right hand side into the same fabric. Once the commissioning is complete, the controller UI will be updated to show the outlet. You can see the switch, light and the previously commissioned outlet on the controller. Now, we can toggle the state of the outlet through the controller. It is also controllable through the phone app. In this way, the controller is able to control a variety of Matter-based devices in your home. Thank you.
Hello and welcome to another Q&A session. And now we have Rishikesh and Piyush to answer the questions. Hey guys, how are you today?
Hello.
We are doing good.
You're good.
Yeah, welcome to DevCon23. We are pretty happy to have you guys here. And we can go now for the first question from the audience. So does the version of Matter developed by Espressif provide support for bridges to other devices such as those using ESP now? Are the code examples for bridges other than Bluetooth or Zigbee?
I'll take this question. So the answer is yes. The Espressif's SDK for Matter, the ESP Matter repository, has a few examples for bridges. Currently, our ESP now to Matter bridge also in there. In addition to that, there is the data model is dynamic, so that you have the ability to create the bridges around the device types that you require on your own. So you can give it a try.
Okay, thank you. So now going to the second question from the audience. If someone has an existing cloud service, can they just integrate the Rainmaker Matter support?
Okay, I'll take this one. So initially our focus was to get the Matter Fabric enabled first in Rainmaker, but we understand that a lot of our customers already have their existing IoT clouds, but they are still looking for Matter support. So we definitely support them on the firmware side, but even on the cloud side, we are actively working on having a variant of Rainmaker, which is specifically only for Matter Fabric, and it would have some cloud-to-cloud integration and authentication so that customers can easily get Fabric as a service into their cloud. So that is definitely on the cards and it will be available soon enough.
Okay, thank you. So, and I like to mention that if you are like interested in knowing more about Matter, we have a pretty nice webinar series. So we have 3 different topics. So like from the device to the certification. So you can check on our YouTube channel, and then you can know more in details how it works, the whole like development process. So let's just check if we have any other question from the audience. I don't think so. We will continue answering the questions by the chat. So if you have any question, you can just please ask us in the chat and we'll answer by text. So I'd like to thank you guys for the talk, for answering all the questions, and I hope you are enjoying Espressif DevCon. Yeah, so we can now go back to the studio.
Next, we have an independent software engineer, Hans Höpfinger from Germany. As we explicitly said in our call for presentations back in February of this year, DevCon is made by developers for developers and is addressed to the entire developer community. Hence, we will not be presenting just the work of Espressif engineers. So Hans's talk is entitled Turning ESP32 into a PLC with the Eclipse for Diag framework. In short, Project Logibus.
According to Franz, there are many hardware solutions out there using ESP32 as a programmable logic controller, but they all lack a real PLC runtime and an integrated development environment. Franz's Logic Bus, on the other hand, integrates Eclipse for Diag, which is an open source project that does provide a runtime called Forte and an IDE. So this solution brings to real PLC features like online watch and online change to the ESP32 ecosystem. So let's take a close look at Franz's project, Logibus.
Hello, ladies and gentlemen. My name is Franz Höpfinger. I talk today about the project Logibus, or turning the ESP32 into a PLC with the 4-diag framework. Whenever you have questions, feel free to ask them in the Q&A box. We will start with an introduction. Then we will see the background of automation systems. Later we will see how 4-diag Forte runs on the ESP32. We will have a look on special hardware. And then we will see application example as well as programming examples. Let's start with the introduction. My name is Franz Höpfinger. I'm a computer scientist. I work as a freelance software developer for HR Agrartechnik, HR Agrotechnik. This company was founded by Christoph Hante and Markus Rensing. Christoph Hante is also a farmer and an agricultural contractor. We will later see why this is important. And this company is mainly focused on isobus control solutions like tire pressure control systems. Let's talk about the background of automation systems. We have always a technical process. So we want to produce some product. May it be material product like a car or immaterial product like a heated house. This process is sensed by sensors and is controlled by actuators. And these sensors are read in by a control systems and the actuators are controlled by a control system. So a control system named a PLC, a programmable logic controller, you can say it's a small computer. And this will be programmed, configured, watched and monitored by a PC. And nowadays we also have the higher level and IoT connectivity like production control systems and so on. Let's talk about the motivation. We want to have a PLC on the ESP32. Hardware-wise, we found a lot of different boards and boxes for ESP32-based PLCs. They are sold everywhere, but programming-wise, most of them are programmed in C, C++, or in the Arduino IDE. There is no real function block-like programming environment. Talk about the hardware. There is really out a lot, like LilyGo. You see it on the left. This is LilyGo. Weidmuller, Seed Studio, and many, many more. There's a but. Most of them have not PSRAM on the ESP32 module. We will later see why this is important. And most have relays, not MOSFETs. If you are familiar with electricity, you know MOSFETs have a higher switching frequency and MOSFETs have less tear and wear. Now talk about the PLC environment. We have out in the market Codesys, we have Logicat, there is an open source one, the Open PLC project, and we have Eclipse for Diag. There are many more, but these 4, we had a closer look on it. So for codices, we found out it's not available on the ESP32. We asked them and they said, no, you must go full stack Linux, minimum a Raspberry Pi or higher. Logicat was willing to give us a FreeRTOS version, but it would be very costly. It would need a lot of porting to the ESP32 because running on FreeRTOS does not directly mean running on ESP32. And so, yeah, it would be possible, but we did not go that way. Then there is the OpenPLC project. You will find this a lot in the internet. It has 2 big drawbacks. It is quite old. It's running on Python 2, not Python 3. You have problems if you want to install it on Linux. And it has no real monitor and watch. So this was really not the solution. And then we found Eclipse for Diag. It's open source, which is nice, and it has an initial ESP32 port available. It was a very basic port, but it was there and it was running. Now talk about PLCs. PLC is a programmable logic controller, as I already said. What we want? We want a one-time flashing of a runtime. A runtime is a project, like you know it, the ESP IDF project, which is compiled together and flashed on the normal way of the serial flasher. And then this runtime runs on the PLC. After this, you transfer the logic of the control over Ethernet or Wi-Fi, also over remote. So you don't need the serial connection. And then you can do monitor, watch, and force for variables and I/O. In a few seconds, I will explain what monitor and watch is. And also important, creation of a boot file. Now I took a line here. For us, it was also important to have isobus support. For many people out there, especially if you are in the building or industrial automation, it will not be important for you. We wanted special functions for the agricultural market, compatibility to ISO 11783 isobus, especially ISO 11783-6. It's a HMI solution for tractors and for agricultural. This said, it's clear we have one version which is good for PLC control, for building automation. This is fully open source, and we will have one version with isobus. This is not fully open source because the isobus library is not open source. So we have 2 versions, open source and open core. Next, talk about Eclipse for Diag. Eclipse for Diag is an open source project. It consists, as all PLC programming environments, of an IDE and a runtime environment, plus, of course, function block library and examples. So the main parts is the IDE and the runtime environment. Let's have a look on the IDE. If you're familiar with Eclipse, you will see that the menu bar, the symbols, the tree view, everything is same than the Eclipse IDE. Here we see the ECC, Execution Control Chart Editor. It's like a state machine, fully graphical programming, or Petrinet. Here we see a function block editor, a function block debugger, and here we see the connection of several function blocks together. We get improvements by time on the ForDiag IDE. Like recently, we got the breadcrumb widget, we got the search box, we got the search result, we got the problems view, and so on. So Eclipse for Diag is developed actively. Next, we want to see monitor and watch. I already said this is one of the most important things on a PLC, to be able to load a model on the PLC, but also to monitor and watch the inputs and outputs of the function block. Here we see a typical situation. We see here this function block has an error, and he says in the status message, hey, I failed to register an observer. Also, force is an important function, so you can click on an input and you can override the variable during runtime. You don't need a JTAG connection to do this, but everything is done over Wi-Fi or Ethernet. Next, there comes a nice gag. UML diagrams are often written very nicely, but the code is written not in the same style, it's written ugly. FreeRTOS avoids this. The model, the nice diagram, directly is executed on the controller. Now, an overview of FreeRTOS Forte. Forte is the runtime system. It runs on many operating systems. Windows, which is not the most destination system because it has no IOs. POSIX systems like Cygwin and Linux. Linux is more important because embedded Linux is often used on embedded controllers. NetOS, ECOS, VxWorks, RCX, PikeOS, and FreeRTOS. This is the reason why we can run it on the ESP32. Here you see a lot of controllers it's running on, and here also are many controllers listed, like for example the Lego Mindstorm. In addition to that, we have a lot of communication interfaces, for example Ethernet PowerLink or OPC UA. And now this list is extended 1 point. We have FreeRTOS Forte also running on the ESP32. There are some requirements to take in account. The model, I think it's common to all PLC systems, the model is always in RAM. So if you have a bigger, larger program model, you need to have the PSRAM. So it runs on all ESP32 derivatives like the ESP32, S2, S3, C3, but it makes more sense to use the ones with PSRAM. Of course, you need Wi-Fi or Ethernet. Wi-Fi comes always with the ESP32. It can be station or access points. That does not matter. You just need an IP address. And we will use the file server for boot project and IOP loading. I will explain it on the next slide. This is the ESP32 file server. It's a standard one from the examples directory on GitHub. And here we can upload the IOP file, which is the Isobus object pool. It's a HMI definition. And here we can upload the fboot file. So after we finish development, we want the system to load the program at boot. And with the boot file, we tell them, hey, take this program and load it at boot. Don't wait for somebody who connects with the IDE. Now we want to see special hardware. We learned already in the beginning that there is a lot of hardware, but sometimes you need special. Special hardware mainly includes that we need a CAN bus usable as isobus, and many of the off-the-shelf controller do not have a CAN bus. So one we developed is the Huginen moped. It's a German funny term. A moped is like a motorbike, and Hugine is a DIN rail. So it's a DIN rail solution. It's based on the M5 stack Atom PSRAM. Why PSRAM we explained already. It has 4 outputs. It's smart switch output, so MOSFETs, not relays, and it is 3 inputs. This is for some applications too less, the 3 inputs. So you can connect here 2 buttons, and then you have here 1 button on the M5 stack directly. So what's in production in the moment is a larger solution. I only have a picture of the PCB layout. They are not arrived, but in production. It's also a thin rail solution. It's based on the ESP32 DevKit C, S2 or S3. You can plug it here. And it has 8 outputs. So here you see always a double output. And it has 8 inputs here. And it has also the CAN bus. I forgot to write it here, but you see here is the CAN bus connector. And it's in production now, so maybe later we will see the products. Then, this is on, we need also outdoor solutions, waterproof solutions. So we also have developed them as well. Here we have 2 derivatives. One is the dual out. You see here the same smart switch we saw earlier, 2 channels output, plus and minus for supply, and a CAN bus. So it's a 2 output controller with Wi-Fi and done. And if you need more than 2 outputs, yeah, we have a dual CAN version. You see here it has 0 outputs. It's as well waterproof. Here it has not the dual output, but this has a second CAN controller. And 1 CAN is for the ISO bus and 1 CAN is for the internal bus. We will see it in the next slide. So the first CAN is the on-chip CAN of ESP32. We go to the ISO bus. Here's the ISO bus connector. And the second CAN is made with a MCP2518FD. You saw it in the picture here. And it goes to the I/O. So this is a 16 output module waterproof, and it has a CAN bus, so we can connect up to 16 of these boards. So we can have 16 by 16 I/Os waterproof, which is really a big machine you can control there. Yeah, and that's hardware solutions. For special hardware, of course, the 4-diag also can be adopted to all hardware solutions I mentioned in the beginning of this speech. Now let's look on some applications. We have made one open source application. So while the IDE is open source and the FreeRTOS is open source, we also made an application open source, which you can load into your 4-diag IDE and use it as a template. So it's this slurry tanker in Austria, beautiful Austria, and it's fully controlled by an aux joystick and by a touchscreen here. The masks here, the graphical user interface is made with the Yetta ISO Designer. This is a GitHub link where you can download this solution. This was a brand new tanker, so the farmer who was wanting this bought it without the control system and directly added this new control system on it. But this is not the only use case. We also can do retrofit to special applications. And now, hold on, it becomes very funny. This is an old controller. You see, it's still a PLC. It's a Klöckner Möller Easy, very old, cabled, long cables, lots of wires, lots of connection terminals, and the operator's box is quite mechanical. So you see a lot of joysticks, a lot of switches, a lot of buttons. And so we switched it to a full touchscreen solution based on 4-diag and the ESP32. So it looks nowadays like this. It's much more beautiful. You have colors, which tells you which function is on and off. Instead, before you only had the switch position for on and off. And so it's much more modern. And on the tractor, it looks like this. So you have here your mapping, your tire control system, your speed, your RTK, and here you have the control of your slurry tanker. So beautiful solution, I would say. To have a comparison for everybody who is not familiar with tractors, here the driver had to look on this box. The box is also limiting the view outside the window, you can imagine. And also it's not so comfortable to grab always set high. And here he has all the functions on the joystick, so every touchscreen button can be mapped on the joystick. He has it in a nice view, and the window is clear view. So I would say nice solution. If you have questions, feel free to enter it in the Q&A box. Now let's look some programming examples. We were asked by one customer, hey, I have also a joystick like this one, but this is a rocker joystick, so it has on-off switches. This joystick has analog axis, 2 analog axes, and he wanted to control a on-off output. Okay, we said that's quite difficult because to have a 0 to 100% axis to 2 outputs, you must do some calculation, and you also want avoid blinking. And we invented this dual hysteresis function block. And this dual hysteresis function block we can see in the next slide. Here we can see the interface of the function block. So you see already every input has a nice description. So the help, when you say so, is included already in the function block. And here you see the ECC, the execution control charge. So from the neutral position, it goes by input larger than mid position plus deadband plus hysteresis to the up position. It goes back if the input is smaller than mid plus dead to the neutral. And the same for down, but with minus. Mid position minus deadband minus hysteresis, down, and input larger than midband minus dead, go back to neutral again. And this can be directly loaded on the controller. No programming of C, C++, and so on. So really a nice model-based and function block-based development. As I said, if you have questions, feel free to enter them in the Q&A box. I will be available for questions after this speech. Thanks for watching. I hope you enjoyed it. Thank you.
Hello and welcome again to another Q&A session. And for this Q&A session, we have here Franz. Hello, Franz. How are you today?
Hello. Fine. Thank you.
Yeah, so it's nice to see you here and being part of the Espressif DevCon. And yeah, so now we can go to the questions. We already have a couple of them here. So let's go to the first one. Is the solution fully open source?
Yeah, the software itself, the 4Diag, is an open source project. So this is open source. Also, our ESP32 port is open source. It's on GitLab. You can write me and I send you the GitLab link. However, I must say the version with Isobus is not open source because we use here a closed source Isobus library. So that variant is not open source, but open core, which is quite common in the industry. So yes and no to this question.
Okay, I see. And talking about the board, so you showed the board. So what about the board? Like you just
I say the board is in production. This was really arriving 2 days after it, and here I have one first assembled prototype. So I'm already testing it. So this is a second version of the Hutchinen moped. And as I explained, the first version, the smaller one, this is in use since long ago. So yeah, the board made its way.
Okay, that's nice to see the progress. And again, is the Gerber and the project free on GitHub?
Yes, some of the boards are free, so especially SIS2, which are made for education purposes. You can find them on GitHub, while the commercial ones, which I showed you, the waterproof ones, these are non-free.
Okay, I see.
So,
yeah. So we have one more question here. So is it functional safety compliant?
Yeah, that's a bad thing. No, because the ESP32 is not compliant to functional safety, and also the 4-diag open source project is not compliant to functional safety. So sorry, no for that question. Maybe an future project for Espressif to bring out the functional safety compliant CPU.
Okay, I see. So we will continue the Q&A in the chat. So if you have any other question, we can answer later. So I would like to, sorry, I think we have one more question. Yeah, sorry. So there is one more question here. So hi, Mr. Franz. What about the secured used in the Wi-Fi data exchange?
Yeah, the Wi-Fi file server I showed is secured with a WPA2 password, but yeah, the password is in the documentation, so we have to do something extra here in the future to secure it more. You're definitely right.
Okay, nice. Okay, so let's just check the chat here again. Okay, so we have more questions here. So how much code overhead was inserted in the ESP32 to make this low code solution?
That's a good question. It's a lot of code. You can watch the repositories. So the 4-diag project is really a lot of code because you have a lot of function blocks which are also available. Low code means you don't need to write a lot of code. You have blocks which predefine function, and all these blocks are a lot of code. Yeah, so it's a lot. Happy to invite you to the project, look the code, test it.
I see. I think we have time for one last question. So we have here one. It's possible to try your project for students in my school?
Yeah, definitely. So if you want to try it without Isobus, you can directly go and try it. If you want to try it with Isobus, especially if you're agricultural school, you have to talk with us. You need to get member in a certain Isobus club, and then you also can try the Isobus version on the school.
Okay, that's really nice. Okay, so thank you for your answers. Thank you for the presentation. It was really, really nice to see. Yeah, that's it. Do you have any other thing to say?
Thank you for watching and wish you a nice day. And thanks for Espressif organizing this DevCon.
Okay, yeah, thank you. So, and now we can go back to the studio.
Next up is Ling Tong, our IoT product manager from Shanghai, who will give a presentation entitled How the Meshlight plus Rainmaker cloud solution works with real use cases. We're really excited about this topic because ESP Meshlight is a new solution by Espressif, which was officially announced only last Friday. ESP Meshlight is an innovative wireless network system that significantly improves the range of Wi-Fi coverage by supporting a large number of devices that can connect to the same network in indoor and outdoor areas. ESP Meshlight provides users with fast, stable, and secure Wi-Fi coverage.
ESP Meshlight is compatible with all Espressif's SoCs starting from ESP32, so ESP32 and ESP32C and S series. ESP Meshlight is a really good solution for scenarios where a lot of devices, a lot of connected devices are spread over large areas, such as smart homes, smart irrigation, smart lighting, solar power generation, and others. In the upcoming talk, you will discover the synergy between ESP Meshlight and the Rainmaker. Lingtong will introduce this merged solution and describe its core features and the workflow. There are some really compelling advantages to it, which you have a chance to witness for the first time ever in real-world use cases. So, Lingtong, over to you.
Today, I'm going to introduce you the solution of ESP Rainmaker plus Meshlight, creating a stable, fast, and maintenance-free network for your devices. Before going into the details, I'm going to share with you some background and context of why we introduce you such a solution. And you may have experienced and tried out different kinds of the mesh for your use cases, driven by BLE, Zigbee, Thread, and the Wi-Fi mesh, and even like the LoRa or the MB IoT. So these all solutions have its pros and cons, depends on your use cases. And one shall evaluate your solution based on the at least below four dimensions: cost, range, power, and maintenance. And we have identified several major pain points in the market by using improperly of the mesh solution and mismatch for their use cases. It's pretty hard for maintenance sometimes for the customer to maintain the mesh network because it's too complex and hard to trace and identify the bugs. And also, on the other hand, it takes maybe extra cost to develop the products in terms of the software development, as well as the options of the chipset could be rather high. And thirdly, insufficient stability. So it means like if you want to reach the longer distance, sometimes you need to sacrifice like the power, and also the stability could be another problematic issue, like losing the signals or the message doesn't deliver to the specific nodes. And the fourth point is about penetration. And especially when it comes to the larger industrial sites, or like even like the household, inside of the house and outside of the house, and how does the signal get penetrated to another site is become a problematic issue when the customer design their mesh solution. So based on which we are trying to introduce you the combination of the Meshlight plus our IoT cloud solution, ESP Rainmaker, and offering you in a more stable manner, easy maintenance, and also in a secure and highly scalable way to develop your own IoT solution in the mesh scenario. The Meshlight is a lightweight mesh network solution based on the 802.11 and TCP protocol, featuring the network self-healing, stable connection, broad signal coverage, and easy maintenance. And on the other side, ESP Rainmaker is a lightweight IoT cloud solution that fully embraces the AWS serverless architecture and can be deployed under your own AWS account. So with this open SDK, you can develop your own IoT solution with a minimum amount of the code efforts and with maximum security and availability. So let's look into a bit about the solution architecture. On the left side, you got all the devices within the mesh network that it can formulate the mesh automatically. And on the other hand, all those mesh devices are connected to the external network. It's assigned with the IP by its parent node and also by the router. And it's discoverable and traceable via the external network. So on the other hand, when you look into the architecture of the ESP Rainmaker cloud, you can see the complete infrastructure on the cloud. The complete infrastructure on the cloud is maintained by the ESP Rainmaker. So as long as you define a clear data model for your own device type, it doesn't matter if it's a lighting device or if it's like the charger station or the solar panel. It's on your decision to decide what kind of the devices that you're going to design in such a mesh solution. And on the other hand, we are integrating the third-party cloud system like the Alexa and also the Google Voice Assistant and the HomeKit. And we also deploy the dashboard under your AWS account as well. So you can manage all those connected devices via the dashboard and see the status, the connected status, and even like the health monitoring of those devices. And you can develop some like the mobile apps based on the REST API, and you can design freely about how the user interactions and the workflows on the application level. So let's look into in a more detailed way of the Meshlight structure. The ESP Meshlight is a set of the solution based on the soft AP and the station mode built upon the 802.11 protocol. So it means like it can formulate multiple downstream connections to based on the soft AP interfaces, while it also supports one upstream connections via the station mode. So it inherently results in the tree topology of the complete network in the mesh solution. So it means like all those nodes in the Meshlight is assigned with the IP addresses by its parent node in order to communicate directly with the external network. So let's look into further those concepts in the Meshlights. We got the root node acting as a bridge between the nodes of the Meshlight network and the external IP network. And all the communication can be going down and up via the root node. And secondly, you got the leaf node. This is like, well, it does not generate further downstream connections, ensuring the network layers will not exceed the limit. So it's on the bottom of the complete mesh network. And we also have the intermediate parent node. We call it child node because it's on the bottom, it's on the middle level of the complete mesh network, as it stands for both the soft AP mode and the station mode. And we also have the concept of the idle node, which is pending, not yet joining the mesh network, and is considered as the idle node. So we also have embedded the root node selection mechanism in the automatic manner as well as the manual mode. So what does it mean? In case in the complete mesh network, the root node gets, say, disconnected. So the complete mesh network maybe go crash. And being the case, we enable the self-healing feature that allows the root node get selected, reselected, but depends on the signal strength relative to the router. And on the other side, sometimes in some use cases, the customer needs to appoint one single root node because the root node could be the screen controller and managing the numerous lighting devices. And so all the devices will get provisioned via that root node. So this is also feasible in our Meshlight network solution. So we have understand the basic concept of the Meshlight, and let's turn around a bit on the ESP Rainmaker, our IoT cloud solution. So as I mentioned, the ESP Rainmaker is an IoT cloud solution that fully built upon the AWS serverless architecture and also embrace the AWS managed services like the User Cognito, Lambda, SES, SQS, SNS, and also S3 DynamoDB API gateway. So what does it mean? It means like you own the high availability and security thanks to these managed services. So the AWS is like the lens and the resource provider, and where Espressif on behalf we build, being just like a contractor, build such a houses for our customer under their AWS account We ensure providing you a great living experience based on all the AWS resources. So starting from a contractor, and later we become a property manager role, because we want to ensure the privacy and independency of the customer's living. But we will ensure you got a good living experience with the sufficient supply on like the electricity and the water supply. So this is the metaphor illustration about how you can leverage the ESP Rainmaker on your business. And to look into further, that we provide a richer feature list on the use cases in the more the end user side, as well as the admin side, the OEM features. So we provide the user management, user device association, scheduling, device sharing, and the remote and the local control, etc. These features are aiming for like the end users use cases and the scenarios, but actually you can develop a lot of a great more end user feature based on the REST API released by the ESP Rainmaker. And on the other side, that you can also enjoy monitoring the numerous of the devices getting connected to the Rainmaker cloud through the dashboard. And you can understand the complete configurations of the backend. So you can even deploy a production field and also the test field. So you can switch easily between the two different modes and building the firmware and the app easily and doesn't impact the production environment. And on the other hand, that you can do some OTA job and maintain your OTA image to the Wi-Fi, MCU, or to your host MCU. That's all feasible through our dashboard. And you can design your indicators that help monitor the device health and also some insights into user behaviors or the device behaviors. So that's pretty flexible and offers you great power to design your IoT solutions. So in general, the value propositions that we draw from the combination of these two different solutions is first, easy maintenance. So it takes only small efforts for the implementation. And the after sales would be super easy for the complete infrastructure, almost none, because you don't need to invest for a team to maintain the cloud, to maintain your firmware, because all the SDK has been maintained and developed by Espressif. So second of all, the low cost. So you can develop the Meshlight solution on our cost-efficient chipset options, and support and development is rather easy, and it takes less efforts for the complete solution design. And we provide you with the complete example guiding you how a mesh devices getting connected to a Rainmaker cloud, the provisioning, and also the controlling, the commands, and also how you design and define device type, the payloads, and also the service and the function parameters. And thirdly, pay as you grow. So what does it mean? So it means like, since ESP Rainmaker is based on AWS serverless architecture, so you don't need to pre-provision any compute resources on AWS cloud, and you don't need to maintain these kind of resources as infrastructure. So even if your business are small, you don't need to worry about paying in advance for these idle resources. So this provides you great flexibility in the beginning and low investments in the initial stage. And the fourth point, which is very important, the independence. So which means that all the data belongings are owned by the customer, not by Espressif. That will ensure that you gain the complete independency for your niche business segments, and including the device and the user data. So let's look into a bit into details how actually the root node commissioning works. Initiated from the app side by establishment of the BLE connections. The app will send the Wi-Fi SSID and password, user ID, secret key, mesh ID random number. And only in the meantime, the root node would generate the soft AP SSID and the password as well. So sending back the root node ID and notifying the soft AP SSID and password will be done in the same time via the BLE connection. And afterwards, the root node device will start going to the cloud, initiate the provisioning process by sending the user ID, secret key, and also the node ID. And at the same time, the pairing of the BLE will be removed from the app side, also from the device side. And the app, once receiving from the node ID information, that will goes to the cloud together with the secret key to acquire the request ID from the cloud in order to check the user node mapping completion status. So after the provisioning is completed, the root node will report the node level information like the mesh ID, random number, soft AP SSID and password, self IP and self MAC. And after the root node get provisioned, you might wonder how the child node commissioning is done. It's pretty much sharing a similar process with just a few exceptions. Let's look into, well, when the BLE connection is done between the child node device and the app will also send the Wi-Fi SSID and password, the mesh ID, random number, user ID, secret key. And the only difference is this soft AP SSID and the password is sent by the app to the child node. So once the child node receives the soft AP SSID and it knows which root node in the mesh network it will going to join. So the child node device, after reporting back the child node ID, it will start joining the mesh network created by that root nodes and assigned with the IP, and it starts with the provisioning and the user node mapping via Rainmaker Cloud. And on the other side, the app will do the same to acquire the request ID to also to check the completion status of the user node mapping. So when the provisioning is done, the node level information will be reported by the child node devices to the root node and the cloud, respectively. So you may wonder how the mesh group is created. And actually, there's the difference definition between the mesh group and the cloud group. So under like the single mesh network, those devices are actually maintained locally. So those devices can be allocated in inside of the house and outside of the houses. And how do you manage and control a specific batch of the devices that are only located in outside of the house, like in the yard? And this is why you need the mesh group under the same mesh network. So it can contains multiple mesh groups in the single mesh networks. And we have integrate that features in the Rainmaker Cloud with our Meshlight solution. Let's look into the workflow. And starting with getting all the node information from the cloud, and the app will start parsing the node information and try to display the group device list. And you will know like all those nodes which can be divided into different mesh groups, and it starts call the API of the groups to create the mesh group with the metadata. So the mesh group ID is kind of the tag to help the root node and the child node understand which mesh group they are in. So this information will be syncing up via the cloud to the root node and the child node respectively. The same with the action commands. If I want to try to control only the devices under a single specific mesh groups, the app shall request to get the mesh group details with the metadata from the Rainmaker Cloud, and the group ID, the node ID, along with the group metadata will be acquired, and also the commands together will with the root node ID, mesh group ID will be sent to the root node devices. So the root node device, once receive this information, it will do the broadcasting to all the child node devices amongst the mesh network. The child node devices who are under that mesh group ID will execute the action commands, while the rest of the devices which are not in that specific mesh group, they receive, but they don't do any execution, but they will do the broadcasting. So that will further extend the range of the signals. So this is extremely beneficial for many applications and scenarios. For example, like the solar panel, the new energy industry segments, and all those panels are installed, for example, on the roof of the houses and shall be managed remotely and also locally. And via the Meshlight plus Rainmaker solution, this can be done easily. And thinking about like a plant growing system, when you have a screen controller that needs to manage all those numerous lighting devices on the different rooms or the areas or the sites, you need to understand, for example, when and how those lighting devices behave in certain time. And you need to manage that information precisely to different type of the lighting devices. And this can also be achieved via the combination of the Meshlight plus Rainmaker. And the thirdly is like the warehouse lighting. It's pretty much, you can think about in such larger sites, sometimes the distance amongst the lighting devices could be far away from each other. So this can also be done via the channel penetration ability and also the distance that the Meshlight can achieve. And this would be really beneficial for the scenarios that I mentioned above. And you can also develop your own solution for some niche use cases as you wish. So before we close the session, we can also look into a short video demos to demonstrate the process as I mentioned above. So starting with the provisioning for the root node. So this is the app built upon the ESP Rainmaker cloud, and it starts searching the root node via the BLE. When the BLE connection is connected, and all those information will be exchanged between the nodes and also the app. And once the provisioning is done, you will see the app will acquire this information via the Rainmaker cloud, and you can see the nodes already getting presented in the main page of the app. And you can see there's a small icon on the right corner. That is also the icon standing for the mesh. And you can do the same actually on the UI side to representing the mesh nodes. And now it's provisioning for the child nodes. And we are demonstrating you the child nodes provisioning under single root node. And pretty much similar process that you see here, that all those child nodes get provisioned completely within that root node mesh. So it's also traceable from the Rainmaker cloud, and you can do the control for the single devices via the Rainmaker. But you can also try to manage the creation of the mesh groups to control those the mesh devices individually. So this is the demos that how you can create mesh groups for the devices that you selected. For example, if you try to select a few of them out of a mesh network and make it the name a light group, and such a mesh group will be created and visualized in the Nova Home app. And you can try to do some actions, some commands on and off here, and you will see the lighting devices will just doing the execution of the commands accordingly. And it doesn't matter if what kind of action commands has been sent via the cloud to the root node, and the root node will be just do the broadcasting to those child nodes. and they will just do the execution accordingly. And the rest of the devices within that mesh network, they receive it, but they don't do any execution, as I just mentioned. Yeah, so this is like the short demo of the video, and you can actually refer to more details of the projects that we open source it on our GitHub. And you can type the keywords ESP Rainmaker or the Meshlight for the projects respectively. And we have the examples for you, and it's ready. Thank you very much. See you next time.
Many thanks to Lingtong for his comprehensive presentation. I actually really liked that one. It was very interesting, wasn't it?
Yeah, it was. The combination of ESP Meshlight and the Rainmaker Cloud seems like it can certainly transform some scenarios that require deployment of multiple devices and networking and group control.
Hang on, what time is it now?
It's nearly 3 p.m. by my watch.
Wow, it's time for our afternoon break. Time flies, doesn't it?
It does.
Cool. So it also seems we're a bit ahead of our schedule, so we can actually take a longer break, which is really nice. Let's take a break, grab a bite and some tea or coffee. We'll see you again in 1 hour and 25 minutes for the last session of today's program.
So basically, we will start the next session at the same time as in the program at 4:20 p.m.
Local time. See you then. Hello everyone. We're back for the last session of Espressif Developer Conference 2023.
Day 1.
Day 1. Yes, I'm Yanis.
I'm Ivan.
And it's so good to be back with you. Next up is a guest speaker from Thistle Technologies, where Ning Shang is VP of Engineering. Thistle Technologies is a security company built for developers, which is headquartered in San Francisco, California. The company specializes in building tools that help connected device manufacturers build security resilience in their devices. Ning Shang's talk is entitled Enabling Secure Boot version 2 on ESP32 platforms in development and production. We'll talk about a methodology aimed at easily signing key security for day-to-day development and for production releases.
In a nutshell, with this methodology, you can create Docker containers that will automatically build and sign images of the application using dummy signing keys. Then there is a web service that can patch the signatures in those generated images with the production signing keys. So this way, the production signing keys are protected by a cloud key management system, and those keys are never exposed either to the build system or to the human operator during the ongoing signing of firmware releases. Both dummy signed and production signed images are readily available for development and production scenarios. And in general, this is a really nice approach to secure the production keys. So let's attend to Ning Shang's presentation.
Hello, my name is Ning. I work at Thistle Technologies. Today, I'm going to talk about enabling Secure Boot v2 on ESP32 platforms in development and in production. Before we start talking about Secure Boot, let me talk about myself briefly. So, I run the engineering team at a company called Thistle Technologies. For my background, I was trained in mathematics and cryptography. I have many years of experiences in building, attacking, and securing the hardware devices and key management systems in production systems. Currently, I work at Thistle to make hardware security easy for IoT device makers. Now let's talk about Secure Boot. Some of you may know the Secure Boot is the boot sequence of software images on the hardware device, in which each software image is loaded and executed only when it's authorized by a previously authorized software image. So in the end, the authorization boils down to a root of trust in hardware. The Secure Boot needs chipset support. Our awesome ESP32 platforms support it. So once Secure Boot is enabled, it cannot be disabled on the same device. So it ensures that only signed firmware images can run on the hardware device. Therefore, it prevents the malware persistence at boot time. So depending on the design you're doing on the ESP32 platforms, so for example, if you are doing a crypto hardware wallet using an ESP32, and you sell this product to your customers, you probably want to get Secure Boot enabled so that nobody can flash arbitrary firmware on your device. So to enable Secure Boot on the hardware device, usually the process is consisting of the following steps. So first of all, we need to create and management firmware signing keys or a public key infrastructure. Second, we need to connect the just created keys to the hardware root of trust. So we need to do a field programming to configure security parameters and the root of trust into hardware. Then we need to properly sign firmware images, because once Secure Boot is enabled, all the images need to be signed in order to run on the device. So to sign a firmware image, we require signing infrastructures usually. So typically, a secure and easy to use signing key management is it's not very easy to do. It's a challenge. We're going to talk about how we can address these challenges in the rest of the presentation. So now let's talk about ESP32. The ESP32 supports secure boot. So it's great that it supports this awesome hardware security feature. The preferred secure boot scheme for ESP32 platforms is the Secure Boot v2. Secure Boot v2 is available from ESP32 revision 3 and later. Also, it's available in other newer ESP32 platforms, including ESP32 S2, S3, etc. Secure Boot v2 is based on public key cryptography. It uses the 3K-bit RSA with the PSS padding to sign the bootloader image and the app image, and they will be verified at boot time by the boot ROM. ESP32 SPv2 supports at least 2 boot flows, which I call ESP IDF and MCU boot and Zephyr OS. Many of you are probably more familiar with the ESP IDF boot flow. It's based on ESP's IDF framework. So you can see the 2 boot flows in the slide. So in terms of the booting process, it's very similar. In the ESP IDF boot flow, the IDF bootloader is used. The boot ROM will load the IDF bootloader. The IDF bootloader will load the app image. In the MCU boot and Zephyr OS based boot flow, the boot ROM will load the MCU boot bootloader, and the MCU boot bootloader will load the Zephyr OS based app image. In terms of secure boot, there are some differences in implementation. In the ESP IDF case, the boot ROM verifies the IDF bootloader using a public key hash burned into eFuse. And the IDF bootloader will verify the FreeRTOS based app image also using the public key hash burned into eFuse. In the ESP32 MCU boot and Zephyr OS case, the boot ROM will verify the MCU boot bootloader using the public hash in eFuse. However, when the MCU boot bootloader verifies the Zephyr OS based app image, it uses a public key embedded into the bootloader, the MCU bootloader itself, to do the verification. Conceptually, these 2 boot flows are very similar, but the implementations are slightly different. So how do we enable Secure Boot v2 on an ESP32 device? In general, there are a few things we need to do. First of all, we need to generate firmware signing keys. This is usually a one-time effort. Once the key is generated, it will be used to sign firmware that runs on the same device over and over again. Then we need to determine an eFuse configuration and blow the eFuses to get secure boot enabled. Again, this is a one-time effort. Once we know how to do it, we'll use the same configuration to fuse the same type of devices in the same product. Third, we need to sign firmware in order to have it run on the secure boot enabled device. So whenever we make a change in the firmware, we need to sign it again so that it can run on the device. So therefore, it's an ongoing effort to do firmware signing. Now let's talk about the signing key generation for Secure Boot v2 enablement. So for local development and testing, we can use OpenSSL or the ESP IDF tool, the ESP secure.py tool, to generate a key pair. And the key pair will be written into files. For production releases, the file-based keys are usually not the best choices. We recommend to use a proper key management system, such as AWS KMS, GCP KMS, and hardware security module-based key management systems. In order to enable secure boot on the ESP32 device, we need to burn eFuses. We need to know which eFuses to burn. There are at least two ways of doing this. The first way is not the recommended way. We can burn the individual eFuse bits based on the values computed from the public key and the handpicked values to enable secure boot. Using the ESP eFuse tool, we don't recommend it because it's easy to make a mistake if we burn individual fuses. If we mess up with one bit, we may break a device. The recommended way for enabling secure boot is to sign the bootloader and the app image bundle with your choice of the private key. Then we flash the signed images and the valid partition table to an unfused ESP32 device. On the first boot, if everything works, if the images and the partition table are valid, the eFuse will be blown by the bootloader to get secure boot v2 enabled. So this is taken care of by the bootloader in one shot, and it only requires the flashing of the images. So that's the recommended way. So as I mentioned before, once secure boot v2 is enabled, only signed images can boot on the device. So we need signing continuously. Now, you probably have realized that the secure boot v2 enablement is largely a firmware signing problem and a key management problem. Because once the firmware images are properly signed, it's a matter of flashing onto the device to get secure boot enabled and to get the firmware run. So there are two cases we want to distinguish. The first one is the signing in development. Usually in development, we only play with a handful of devices. The signing key confidentiality is usually not very critical because these devices will not be used in the production scenario, will not be in the hands of the customers. So the signing process should be very easy to allow a fast iteration. So if there's a bug in the firmware, we want to be able to easily sign the firmware and get it run and test it on the development unit. For production signing, the situation can be a little different. If you are producing a design and you're selling the finished devices using ESP32, in many units, if you are selling thousands of devices to a customer, you probably don't want to get the signing key leaked so that an attacker can sign your firmware, can sign any firmware that runs on the device that you sell. So we should not expose the signing key in the production signing scenario. But still, the signing process should be easy to allow fast releases. If there's a bug in the firmware, or if there's a new feature available in the firmware, you want to be able to quickly release the firmware. In both cases, it's desirable to have the production firmware very close to development firmware, so that what is tested in development can be reflected in production. So therefore, in terms of production images and the development images, ideally they should only differ only on public keys and signatures for secure boot enabled devices. Okay, so in the rest of the presentation, we're going to talk about how to sign firmware in development and in production to enable secure boot v2 for ESP32 platforms. So signing in development can be done in this way. So first, we generate file-based private signing keys using using software tools like OpenSSL or the IDF tool. Then we use the menu config to enable secure boot v2. We will configure the signing key file in menu config, and also save the SDK config file for later use. Now we can use the ITF build command to build and sign an application with the saved SDK config. So we'll be signing a void app. I'm going to talk about the void app in the following slide. So once everything is signed, we can just flash the bootloader and the app image onto the device to get secure boot enabled on first boot. So development signing keys are usually not very security critical, and sometimes it's okay to check them into a version control system for easier access and for better backup. So here, like we are showing a couple of the important, like the most important configurations for enabling secure boot. From menu config. Usually on secure boot enabled devices, we also recommend to disable JTAG, but enable secure ROM download mode on ESP32 S2 or S3, like when they are available, so that we can also flash the signed firmware onto the devices. Yeah, so once menu config is used to enable secure boot, we save the SDK config. Then we can use the SDK config to build a void app. So a void app is an app that I wrote that CISO is open sourcing as well. So it's an app that does not do much. So you can see like there's only a few lines in the source code of the app. Essentially, it prints out a message to the console. It does not do anything, but once it's signed, it can be flashed on an ESP32 chip to blow the security relevant bits to enable secure boot and other security features. A minimum fuse blower void app is very important in the production scenario because by doing nothing, it exposes no attack surface to a production device. So that's how you can sign firmware in development manually. And this process can be further automated into a one-click setup. So my company CISO has released the developer tools, including a bunch of Docker files, the pre-built Docker images, and utility apps, including the void app, to allow a one-click firmware signing in development. So here is the GitHub repo that we open sourced to allow this to happen. So firmware signing essentially becomes one command, one Docker build command, which you can see here. So you can override the SDK config and your private key as build arguments in Docker build. Now I'm going to show a video demo of development firmware signing using the Docker image. So first of all, we will clone the GitHub repo I just talked about. So once the repo is cloned, we change into the ESP32 directory and run the docker build command. It'll take a few minutes. The Docker image is cached, so it's really fast in the demo. So these are the two build parameters that can be overridden to allow you to insert your own SDK config and your private key. So once the Docker image is built, the bootloader and the app images are signed automatically inside it. So we will activate the IDF environment so that we can flash the images onto the device. Now the IDF environment is activated, and the device is the device connected to the host machine running Docker. So that's ESP32. So now let's use the Void app. So before we flash the app, let's see what's happening on the board. Now seems like flash is totally erased. There's nothing on flash. Of course, we get invalid header. So that's normal. Now we are going to flash the signed bootloader image from the Docker container. Okay, the bootloader image is it's flashed onto the device. We're going to flash the partition table and the app image. Okay, now the flash program is done. So let's see what's happening on the device. Okay, good sign. We see this message. I'm the Void app. I do nothing. So the image has the app has booted. If we look more carefully, we can see that the secure boot is also enabled. From the console output, and this message is about the app image verification by the firmware bootloader. So we have secure boot enabled, and the signed images are up and running. That's a demo for doing development signing for ESP32. Now let's talk about the firmware signing in production. There are many reasons the file-based signing keys are not very suitable for production signing case. So we can't easily use the build system, the ESP32 build system, to load a private key from file system to sign a production image if you want to protect the key. The reason file-based signing keys are not suitable is because they can be exposed by human beings or by malware. So some of you may still remember the recent firmware signing key leak from MSI. So we don't want to do that. We don't want to use file-based keys. Then what do we do? So we have a few requirements for signing firmware in production. On the security side, we want the production signing keys not to be exposed to any human operator or software. On the usability side, we still want the day-to-day signing operations to be smooth. So if every signing operation requires a ceremony to go to a safe to fetch a key, it's very inconvenient. So CISO has a solution. Based on a KMS backed the production signing keys. So essentially, we are providing a service, a firmware signing and patching service to use KMS protected keys. So the idea is that we manage the firmware signing key in the proper key management system. in this case, the key is generated in the system and also the managed in the system. No one, including Thistle, has access to the keys, but the key management system can be used as an oracle to do the signing operations without leaking the private key. So conceptually, our idea is this: so the input will be ESP32 firmware image, signed using the development signing method you saw earlier. Then this image will be uploaded to the service, will be sent to the service. The service will parse the image, extract the signature block. It will use the production signing key in KMS, in the key management system, to sign the payload, the content of the image, and replace the development signed signature block with the production signed signature block. So the image, so these two images will be almost identical, and the only difference is in the signature block. So that's the idea. That's how we propose to solve the problem. And in brief, we implemented a system, shown in this slide. So it's a firmware signing system, consisting a few microservices. So we have an IAM service to do user management, to do user management and access control, and also the signing configuration. The firmware patching service deals with parsing and patching firmware images. It has no access to cryptography related operations. For cryptography related operations, we have a code signing service, which will use a KMS. So our implementation is based on GCP KMS. So the code signing service will use the KMS, the managed production signing key, to sign a digest and produce the signature block. It will give the signature block to the firmware patching service to patch and get the production signed image in the output bucket. So that's how it works. We don't get the signing key exposed to any entity outside of the KMS. So our ESP32 Secure Boot v2 production signing system supports both the ESP IDF boot flow and the IMCU boot ZephyrOS based secure boot flow. Now I'm going to show you a demo of doing production signing using the Thistle system. So in order for you to use the system, you just need to go to the Thistle website, sign up to get an account, then log in. Once you are logged in, you can create a project in which the firmware bundle will be uploaded. So we just call the project DevCon23 demo, and it's for production signing of ESP32 firmware. Once you click the button of create secure boot signing key, a key pair will be created in the KMS. Now you can enter the project. Yeah, what happened here is that in the project, you can upload your boot image and app image. There's a secure boot feature. And in settings, you can also get the public key, for the key generated in KMS. Only the public key is available here, so you can use the key to do the verification independently if you wish. The private key is never exposed. Now let's go to the secure boot field and upload a firmware bundle. Yeah, we call it a dummy signed IDF firmware. so these firmware images are signed using the previously mentioned method in development. So let's upload the bootloader image and the app image. Once we click on the upload button, the backend will start processing these images, doing the signing and patching, and put them to a place for you to download. Now the signing is done. These 2 production signed and patched images are available for you to download, and they are readily flashable to your unfused or secure boot enabled devices to enable secure boot. Okay, that's the end of my presentation. I'd like to thank Thistle Technologies for supporting this work, and also my colleagues at Thistle for their feedback. In particular, I'd like to thank Pierre for telling me about Espressif DevCon, and I'd like to thank Toru and Russell for helping build the production firmware signing service. This presentation can also be viewed from this link at the bottom of this slide. Thank you very much. Now I'm ready to take questions.
Hello, everyone, and welcome back to another Q&A session. Now we have Ning to answer all your questions. Hi, Ning. How are you today?
Good, good. How are you guys?
Yeah, very good. So welcome to DevCon23, and thank you for your talk. So now we can go for and answer the questions. So we have 3 questions from the same participant. So I'm pretty happy that we have active participants here. So thank you for being that active. So the first question is SBV2 must be used together with flash memory encryption?
It's not necessary to use the SBV2 together with flash memory encryption, but no, like both are doing slightly different things. No, both are good for security, but no, for as many security mechanisms or countermeasures, they are restrictions to put on the device. So I think this question is actually related to the second question that you posted on the channel. Is it sufficient to enable partition encryption and encrypted NVIS in smart home devices, or is it better to enable SBV2 in addition? So no, these are 2 different security mechanisms. Secure boot V2 or secure boot is for the integrity protection of the firmware. It makes sure that only the signer, only the owner of the device, who has the signing keys or access to the signing key, can flash a firmware that can run on the device. For flash encryption or like the firmware encryption, the threat model is for confidentiality protection. So in one version, for example, in one version of a flash encryption, you still can flash like the plain text firmware, but the plain text firmware will be encrypted in space on the device with a key, already burned into fuses on the device. So therefore, it'll be very hard for anybody to extract the flash content and see the plain text firmware, but still anybody can flash plain text firmware, for example, containing a piece of malware. So they are doing slightly different things. So it depends on usually to decide whether to enable secure boot or flash encryption. I think you need to do maybe a mini threat model to see what's the best for you. So to answer a question about whether it's a good thing to enable smart home flash encryption or secure boot in smart home devices, I think it depends on some trade-off decisions you have. So for example, like if this smart home device is meant for for hobbyists, if it's an open source project, I want to play with it at home. Nobody else has access to my to my home devices. And if I still want to later give this device maybe to a friend to use, but I don't want to give the key to them. You have to think twice, whether you want to enable secure boot or not, because you must have the key for your friend, to repurpose the device to do their own firmware and flash on it. It's the same with flash, with partition encryption, because you still have another key to manage for flash encryption. But if you are, so for example, if you are making a business, you are using ESP32 to write a smart home device that you can sell at Best Buy, I'm in the US, so at Best Buy is popular in here. You can want to sell it on Amazon, and if in the smart home device it has it collects information about home, about personal information, you may not want to have a piece of malware running on the system, flashed onto the device. So for the protection of the user, it might be a good idea actually for you to encrypt, to enable secure boot. So only the firmware issued by the developer, by you, can run on this device. So again, secure boot and flash encryption are two slightly different security mechanisms. If you enable both, you get the maximum security, but also they are restrictions to the system. So it restricts who can flash the firmware and how transferable that piece of ESP32 chip is.
Okay, so I say thank you for the very detailed answer. We have one more question from the same participant. So prod sign with KMS works with app image for use via OTA?
Oh, absolutely, absolutely. So on a secure boot enabled device, a prod signed app image, also including the bootloader image, if for any reason, you are reflashing the bootloader image. I know many people don't do that. Once the bootloader image is there, stays there, but the app image gets updated more frequently. So it's the same actually for both images. It works with it works for OTA. So if you still remember the prod sign demo, so when you download that prod sign app image from the Thistle portal, the secure boot portal, it can be readily included into your OTA bundle to flash into your as an OTA image to push to your device. I think in the demo, you kind of have to download it manually and include it into OTA. In the near future, very near future, the Thistle system can make that process really a one-click thing. So you will be able to select the secure boot signed app image from the Thistle portal, and Thistle has an OTA solution that will allow you to push to do the OTA directly from the web app.
Okay, I see. So thanks again. Do you have anything else to share? Any news? Since this talk was pre-recorded, so do you have any news since then?
That's right. If you look at the presentation, now I think it's the same setting. I'm in the same room, but my hair is longer. So the talk was pre-recorded. So in the presentation, when I did the prod signing presentation, I had to use if you really read carefully, you see I have to use the experimental view, because we kind of had that at the Canary release at that time. So it was not in production yet, but ever since that, this feature has been shipped in production. So if you go to like HTTPS CISO.tech and get account, you will be able to see a secure boot in the option on the left hand side of the menu. So everything is shipped in production. If you want to play with it, I also wrote a couple blog posts to guide you through the process of doing that. So I will include all the information in the presentation slides, which I also posted to the chat, to the YouTube channel, so you can get all the information.
Yeah, and then later we will share all the presentations individually, and we can add this link to the video details, or we can ping as a comment as well. So if you are looking forward to get this presentation, you will see later in the individual videos. So thank you so much, and I hope you enjoyed DevCon. And now, sorry, you have any?
Oh, thank you. Thank you. It's a pleasure to join the DevCon.
Good. I'm glad you enjoyed. So now we can go back to the studio.
Coming up is a joint presentation by two of Espressif's embedded software engineers, Scott Mabin and Uri Sadel. The guys will talk about Rust async and bare metal on ESP chips. Async in Rust is the mechanism for single-threaded concurrency. The nice thing about async in Rust is that the code still reads like linear, synchronous code, so it's easy to understand. And another nice advantage of async in Rust is that compared to other approaches like traditional RTOS, you don't have to waste lots of precious RAM to allocate a bunch of stacks for different tasks if you want to do multiple things. So this clearly is really interesting for embedded systems. Scott and Uri will explain async in bare metal Rust and show you the functionality in a demo.
Rust on Espressif chips has gained momentum over the last few years, not just due to the hard work of the engineers working on this project at Espressif, but also due to contributions coming from community members. This is really exciting and humbling to see, and we can't thank the community enough. If you're interested in getting involved or just want to see what we're up to, come say hi on the ESPRS Matrix channel. But before that, let's listen to what Scott and Uri have to share with all of you today.
Hi folks, my name is Scott Mabin. I'm joined by my colleague Uri Sadel, and today we're going to talk about async Rust for embedded systems. So what are the goals of this presentation? We're going to explore how async Rust works, apply it to an embedded context. Finally, we'll show off a working application that leverages async Rust. First of all, why would you want to use async? It provides a mechanism for single-threaded concurrency, so being able to do multiple things with a single thread. And because of this property, it can run on a single stack, which is great for resource-constrained microcontrollers. It will also have the ability to write asynchronous code that has similar ergonomics and readability as synchronous code, as we'll explore later in this presentation. So if you didn't see it already, I spoke a bit about Rust on Espressif chips and mentioned async in the talk last year at the last DevCon, so check that out if you haven't. But in short, async in Rust adds two new keywords to the language, async and await. Async defines a block or a function to be asynchronous, and await defines yield points within that block or function to yield. So if we take this example function here, so we have an async function called sayHello, which takes a reference to a UR. And inside here, we set up the message to hello world, and we write the bytes out to the UART. At the point of this await call, the function pauses or yields here, where the hardware is actually transferring the bytes, and other things can run or even go to sleep. Again, once the UART has finished transferring the bytes, we resume the function here, set up the next message, which is goodbye, and do the same thing again. We get the UART to write the bytes out and wait here until it's done. Let's think of a simple scenario to compare various approaches. So for example, reading the state of a button connected to a pin, and depending on the state of the button, turn the LED on or off. Let's look at a trivial busy loop example. So here we set up the 2 pins. We put the LED into an output mode, put the button into an input mode, and all we do is in a loop repeatedly check the button state, and depending on the button state, either set the LED high or low. This is obviously very simple to implement and very easy to read, but it's very inefficient. We're using 100% of CPU power just checking that button state and changing the LED state. Let's try and leverage the hardware. Let's use some interrupts. So again, in this example, we define our 2 pins, but this time on the button, we have 2 additional calls to listen for the falling edge and the rising edge. We then enable the interrupt and then drop into the main loop. Before I explain the main loop, I'll also explain the 2 statics that we define at the top here. The first one is the button, which we'll need global access to the button in our interrupt handler, and a state, which represents the virtual state of the button, which we'll also need in our interrupt handler. When we drop into the loop, we check the virtual state of the button. And if it's set to high, we set the LED high, and if it's set to low, we set the LED to low, and then we sleep. And this sleep mode, in this specific case, will put the CPU in a mode where it's using less power until an interrupt occurs. So when someone presses the button, this is the interrupt handling code that will fire. So the hardware will run this code, and all we do in here is take our button, we clear the interrupt so we don't repeatedly call this interrupt over and over. We then check the state of the button, and then update our virtual state of the button inside here. So if the button was pressed, state is now true. If we come back here, we are at the sleeping line, and now the interrupts happen, it's been serviced, we wake up. We know that state's just been set to true because we pressed the button. So when we check it, we'll set the LED high and then go back to sleep. And then when someone releases the button, we wake up again, check the state, and it will now be low. We set it to low and go back to sleep. This is obviously much more efficient than the busy loop approach. We now have the option to do other things or sleep in this case. However, it's hard to follow the program flow of execution. Just then, as I was explaining it, I had to go back and forth between the main loop code and the interrupt handler. It's quite hard to understand what's going on. Let's look at an async example. So first off, big difference is main is now an async function. Again, we define our 2 pins and then drop into the loop. Now the main loop looks a little bit different. So we have a select statement, which select will basically wait for 2 things to happen and tell you which one happens first. So here we're waiting for either the wait for rising edge event to happen or the wait for falling edge to happen here. As soon as we call await, this function freezes until one of these events resolves. So this means that we can either go to sleep, run other tasks whilst this is waiting to happen. So in the case where the button is pressed, the wait for rising edge event will resolve, and then we'll execute the first match arm of this match statement, which will set the LED high. We'll go background into the loop and wait for the 2 events, once more. So when the pin is released, the falling edge, when the button is released, the falling edge will resolve and will execute the second one, turning off the LED. Structurally, the async example was very similar to the busy loop, but with async, each await point allows the CPU to do something else or even save power. So essentially, we get the best of both worlds. We get the ergonomics of the busy loop with the efficiency of the interrupt example. And behind the scenes, async will actually use interrupts, but it's hidden away, so the users don't have to worry about that. How does async actually work? Well, you can only await something that implements the future trait, and the future trait has one method, poll, which returns either poll ready if the asynchronous operation is completed, or poll pending if it needs to be polled again later. This is what the future trait looks like in Rust code. Async's relationship with future is an important one to point out, because async functions are actually compiled down to state machines by the compiler, which implement the future trait. And this means that the future trait is the building block for any asynchronous operation in Rust. This is important to note because throughout this talk, I'm going to use future and async somewhat in the same context. And basically, every async function is a future, and other things can be futures as well if you implement them manually. When should you poll a future? You could just poll them continuously. Much like the busy loop example, we could just sit there in a loop and wait until a future returns poll ready. However, this is not very efficient, as we use 100% of CPU, just like the busy loop example. And given that we are going to the effort of implementing the future trait for our types or using async functions, we'd like to do other things whilst also waiting for one thing to complete. This is where the waker concept is introduced. Waker is something that can be used to signal that a future should be polled again. And waking a waker can happen from anywhere. Some examples being an interrupt handler, like in our button and LED example from earlier, a callback function, or just another function. This is a pseudocode socket read implementation of the future trait. I'm just showing you this to give you a idea of the life cycle of a future. When a future is created and executed, the poll method will be called once. Inside this poll method, we check, do we have data to read? If we do, great, we can early exit and return poll ready with the data. However, if we don't, we then need to set up some mechanism called poll on this feature again in the future. So this set readable callback registers a waker, and behind the scenes in this pseudocode implementation, it could be a operating system callback to say, yep, there's data in the socket. And once we've done that, we return poll pending. So when the OS actually runs that callback to say there's data in the socket, poll will be called again. We then check if we have data, and then we return poll ready. So how do we actually run futures? We've covered how they work, but where do poll pending futures actually yield to? They yield back to something called the executor. And the executor is just a mechanism to run futures. It handles the response to wake events and then polls the relevant future again. Executor is a general term. There's no trait or contract for them in Rust, and they can be implemented in various different ways and have various different features and limitations. One popular executor for embedded systems is the Embassy executor from the Embassy project. It aims to provide not just an executor, but a collection of tools and utilities to create effective async applications. Usually the top level future It's called a task. Within a task, many futures may be awaited, but the top level one, the one that is spawned on the executor initially, is colloquially known as a task. In Embassy, tasks are statically allocated to avoid the need of an allocator. And fortunately, the MC executor task macro will take care of this for us, so we don't have to size up our statics or anything like that. Tasks are allowed to have infinite loops, much like a traditional RTOS task, but must contain at least one await point to avoid blocking other tasks. I'll now hand over to my colleague Uri Sadel, who's going to walk through building an IoT temperature sensing data logger that leverages Async.
So hello everyone, my name is Uri Sadel, and I would like to go through our hello world kind of example for IoT. But before that, I would like to talk briefly about what is bare metal or no STD. Well, by default, each Rust program is compiled or linked with a standard library or STD. And for some cases, especially embedded development or kernel development, we sometimes want to use no STD. So how we can actually tell Rust compiler that we don't want to use standard library, but we want to use something else, which is called the core library. Core library is like a collection of basic functionalities and is a subset of the standard library. And we can do that with attribute or macro attribute no STD, which is the first line. So with this, it's first step for bare metal program, and then we have to also specify where our program should start running, and we can do that with no main and entry macro. With entry macro, we basically set where the entry point to our program is, and because when we do not have standard library or operating system, we have to do these things manually by ourselves. So that's why we have to set these things. And also we have to set panic handler. Panic in Rust is when unrecoverable error occurs. So we have to specify what must be done when such event occurs. So now about the demo. Our demo consists of 3 steps. The first step is to initialize and connect to Wi-Fi. Second step is to initialize and create MQTT client and connect to the broker. And the final step is to initialize temperature sensor, get temperature, and send it to the MQTT via Wi-Fi. What we need, we use the Rust board or C3, ESP32 C3 board, and BMP 180 pressure sensor. Okay, so now we are in the Visual Studio Code, and as we can see, the first 2 lines are, as I showed you 2 slides ago, no STD and no main. So basically, we are kind of ready with a bare metal program. Then here on the second window, we have the entry macro. So we are specifying explicitly specifying where should our program start executing, and also we are using our own panic handler, which is ESP backtrace. Like usually this comes as a standalone or external crate. So regarding the code, we have a bunch of imports here. These ones are from hardware abstraction layer and are related for clocks, I2C, and stuff like that, like the basic hardware peripherals on the chip. Then we have this imports for ESP Wi-Fi, some configuration, like Wi-Fi device, and so on. Same for Embassy executor and async stuff. And then we have our sensor and Rust MQTT. So I will continue now with main function. So at this point, like this thing will be like executed like in blocking fashion. So for now, it's still no async application. So we firstly initialize the clock. We are using the maximal frequency for the C3, which is 160 megahertz. Then we are disabling watchdogs. Then we are initializing Wi-Fi, radio, so on, initializing embassy, starting Wi-Fi, and initializing I2C, because BMP180 sensor is communicating via with C3 chip via I2C communication protocol, and stack, enabling interrupts for I2C. And at this point, we are initializing and starting embassy, and this part is becoming async. In our demo, we have 3 tasks, and I will go to them and walk through them. So the first task is regarding Wi-Fi. So first, we are checking the state of ESP Wi-Fi. If we are connected, then we just like going through this and waiting for some disconnected state. For example, if our Wi-Fi router stopped working and so on. But on the first run, we skip this match and we continue with this. If Wi-Fi started correctly, we can send Wi-Fi credentials as SSID and password that we have to set as environment variables here before running the code. And so we have credentials ready. We can continue setting configuration, and we can finally start and connect to the Wi-Fi. If everything goes okay, we should be ready with Wi-Fi. Second task, it's like background task or helper task, which is checking for packets. And when new packets arise, it and process them. It's basically a wrapper of small TCP. And last, async task, which is our main basically task. We are checking or waiting until Wi-Fi is connected. Then we are waiting for DHCP IP address, creating a socket, and we are using public MQTT broker by HiMQ. So this is the host address. So we want to get an IP address from this address. If we get the IP address, we can create a remote endpoint. We are using port 1883, and we can finally establish the connection and create a configuration for MQTT and connect and subscribe to the MQTT broker. If everything is ready, we should be communicating with MQTT broker, and the last step is to create and initialize BMP sensor, start measurement, and start publishing temperature to the MQTT broker. So right now, I will try to run the code. So now I would like to flash the actual code and show you how it should look like. Okay. We are getting some logs. We are waiting for Wi-Fi, for IP address. Sometimes it takes a little bit more time. Okay, we finally got IP address, and now we are getting the temperature. So now I can go to the public HiveQ MQTT broker, and we can connect from here, and we should get the temperature data sent here. So we'll create the connection. We'll add the topic. I put some random name for the topic, so we are the only ones getting messages here, and we are good. And we are getting the temperature. If I touch the sensor, the temperature should go up Yes, 28, 30, and so on. Okay, so that's the demo I wanted to show you. Okay, so this is the end of our talk. Here we have some links which are related to our talk. Thank you for listening, thank you for watching, and if you have any questions, please feel free to write to the chat or ask us during live Q&A. Thank you very much.
Today's last, but certainly not least, is the talk from our guest speaker, Richard Barry, the original author of FreeRTOS and a senior principal engineer at Amazon Web Services. His talk is entitled Refactoring FreeRTOS for the Next 20 Years. The FreeRTOS project started 20 years ago and has since become one of the most popular RTOS of all time. In his talk, Richard will explore the next 20 years of FreeRTOS with Amazon's involvement, including the design, technical roadmap, and distribution philosophy.
The collaboration between AWS and Espressif has been going on for many years and has only become stronger over time. What started with a few special pop-up events and workshops has led to a full-scale cooperation, including ESP Rainmaker, Espressif's ACS solution, and Espressif's AWS IoT ExpressLink solution, to name but a few examples. In light of Espressif's collaboration with AWS, we certainly look forward to hearing what Richard Barry has to say about refactoring FreeRTOS for the next 20 years.
Hi, my name is Richard Barry. I work for AWS IoT. I'm best known as the original author of FreeRTOS, and my presentation is about refactoring FreeRTOS for the next 20 years. So about 20 years ago, after researching different operating systems for a project I was working on, because I thought it would be fun, because I'm a geek, I thought I would write one myself. That project became FreeRTOS. Little did I know at the time it was going to consume the rest of, the next 20 years of my life up till now and hopefully in the future. I now work for AWS IoT, that's Amazon Web Services, Internet of Things. Still very much involved in FreeRTOS as it is part of AWS's kind of edge to cloud software continuum. Today I will talk a little bit about Amazon's involvement in FreeRTOS and also how we very consciously try and keep an air gap between the generic FreeRTOS product, which is not tied to anything, actually, as you'll hear in this talk, especially not specifically any cloud service, and the software which is Amazon specific. Today we are going to look at the roadmap for FreeRTOS, starting with some of the milestones in the past. We look at the past because it gives me an opportunity to talk about the rationale for the various different milestones, and then we can extrapolate those forwards. And also talk about how the kind of design and distribution philosophy for FreeRTOS has come about. We'll then look at how we are applying that philosophy to features that are being developed right now, before looking at the next version of FreeRTOS, which is pretty well determined already, and our intentions for FreeRTOS version 12. We're on version 10 at the moment. So real-time operating systems, or RTOSs, come in various different sizes. You can think of very rich operating systems like Linux and QNX, VxWorks, that kind of thing. FreeRTOS is at the opposite end, is deliberately small. You can think of it really as a library that implements multi-threading. Very focused on the small end, although it does get used on 8, 16, 32, 64-bit, but the ESP32 kind of category of microprocessor is its sweet spot. Okay, so the first milestone to talk about is actually when FreeRTOS was put into a public repository, a publicly accessible repository. When we started FreeRTOS, we were really designing on or implementing ports for very small devices. It's very good for learning how to do it, but those devices were too constrained to really warrant an operating system. They couldn't run an application which was complex enough to warrant multi-threading. When we started porting to 32-bit architectures, then that changed, and FreeRTOS became useful in like commercial products and started to take off. When it got to about 2,000 downloads a month, we moved it into SourceForge. It was getting too expensive to host it ourselves. So SourceForge, in SVN in SourceForge actually, so this predates Git, it predates GitHub. SourceForge serves extremely well. The data you can see on the screen here, the number of downloads a month over the years, that comes directly from SourceForge. You can just go and have a look at that. So really the driver for this milestone was that technology fit. It was the 32-bit architectures were the sweet spot for a very small real-time scheduler, if you think of it that way. The real-time part means that it kind of classifies the scheduling algorithm. It means that there's a deterministic amount of time between an event occurring in the environment and that event being processed. I'm also showing here the code structure that we put into SVN originally. Here we have the source code for the kernel. Then we had a whole load of demos as well. I think at its peak, there were something like 40 architectures and 18 compilers. Some of those architectures are obsolete now, so there's slightly fewer. Just for a laugh, I thought I'd show you what the web page looked like in 2004. This is what the internet looked like then. I drew that logo, so I'm not very proud of that. Interestingly, that entire website was generated using Doxygen, just from Doxygen comments in the C and header files. So the next milestone of interest is the release of OpenRTOS, which is a commercially licensed version of FreeRTOS. Why would we do that? Well, FreeRTOS is open source, but some companies just require a commercial license for whatever internal procedural regions they have. Now, at the time, I was working with Wittgenstein, working for Wittgenstein High Integrity Systems on the safety critical version, which is SafeRTOS. So whilst my company wasn't really set up to do commercial licensing, Wittgenstein had the expertise in the code, so we licensed Wittgenstein to be able to sell FreeRTOS code, but under a commercial license. Moving on then to 2013, this milestone is really driven by, as you can expect in open source projects, kind of removing pain points. This was not only pain points for our users, but also pain points for us trying to support those users. We're very proud of the level of support we can give. And what we were finding was that FreeRTOS was getting integrated with lots of different libraries, and people were coming for support with third-party code integrated with a third-party code with a third-party integration plus their source code. And of course, if anything goes wrong in that bundle of source code, they blame the operating system. What else could it possibly be? It wasn't very satisfactory for them, wasn't very satisfactory for us. So by adding in additional libraries, we were removing those pain points from our user base, because the support team were also able to provide a much better level of support. Very significant here then is 2016. This is where AWS started to take stewardship of FreeRTOS. May not be immediately obvious why, but when you consider that Amazon Web Services Internet of Things, which is what AWS IoT stands for, there are IoT-specific services in AWS, and there are millions of devices that run FreeRTOS that connect to those IoT-specific services. So Amazon are very motivated to make sure that those devices can connect as quickly and securely as possible. This was really driven by market trends on the FreeRTOS side. So this is the driver for this change, if you like. And to do with scalability, IoT requires a lot more software, as we will come on to see. And this extra investment enables the software to be created. Like I say, I will talk a little bit later about how we air gap what's Amazon specific and what isn't, because FreeRTOS is kind of cloud neutral of anything actually product, despite what you might read about the place. So we were very comfortable working with Amazon because Amazon are also motivated to make sure that we maintain the philosophy of running on the latest hardware and making sure that we are providing examples for whatever contemporary projects people are working on. Now, one of the first things that Amazon did was massively simplify the license. They're adding benefits straight away. We had, they changed it to an NIT license, which is extremely well known. It's only 10 lines long. Once you compile your code, the old license and the NIT give you basically the same rights anyway, but the old license was like 1,000 lines or something. So it's a huge benefit just to change to something that people know and is very short. Other things that you may not be aware of that Amazon are doing, which adds huge benefit to the entire community, with open source MIT licensed code. So there's no tie-in. You don't have to be an Amazon customer, of course. So the whole community now benefits from Amazon's security experts. So things like pen testing, AppSec reviews. Something we're excited about is the memory safety proofs that are performed on the code. We lean on Amazon's engineering a lot to provide all those things and then just open source it. Of course, Amazon are motivated themselves to make sure these things are done, but everybody wins. More visible is the long-term support. So there's like 2 years for free. And then if you want to extend that obviously costs Amazon money to go beyond 2 years. You can extend it to a full 12 years, but that part is commercial. Okay, so the next milestone here also gives me an opportunity to talk a little bit about how our design and distribution philosophy has changed or evolved over the time. And this change is really driven by just the huge diversity that software diversity of, let me think, all the different technologies that we have to support. So I think there's, like I say, at one point there was 18 compilers. Some of them are obsolete now. There's all the different architectures that are supported, something like 40 odd at one point. Again, some of those are obsolete. There's is your project a brand new project? Are you adding code to a different project? What's your directory structure? What's your workflow? All of these different variables. So the way that we decided was the most useful for people was to adopt a policy of what we call being deliberately unopinionated. We're not going to offer any opinion or constraint in how you can use the software in your product. That will make a little bit more sense when we come on to the next few slides. So one of the things we did, as I say here on the first yellow point, is moving to Git. And well, it's in Git already, but moving to Git, probably very belatedly, admittedly, as the primary development source, where we were actually working on the code. So we kind of looked at this directory structure before. Now, this is what we call the classic FreeRTOS distribution. Now there are additional libraries in there, but this is still where the kernel is. Oh, let's see, probably, let's do this. This is where the libraries are. This is where the kernel is. So we moved the kernel into its own repository, as we did for all of these other libraries as well. So what does this do to our statistics? Well, you can see there's a bit of an elbow here. Yellow is the statistics coming from Git. There's a different gradient there because we're measuring something else. What we're not sure about yet is this huge spike of noise here. Is this just going to be normal now? Until we've got more data, we're really not going to know. So what does this look like in Git? What I'm showing here is the FreeRTOS organization in GitHub. Each of these pale blue boxes are individual libraries within Git. They're deliberately small, deliberately simple, and don't have any dependencies other than a few functions in the standard C library. We still have a repository which has the classic distribution, but now what these dotted lines are supposed to show is those libraries are submoduled into that. Now, there's nothing here which is AWS specific, right? These are just standard protocols. So how do we, this is how we keep that very clear delineation between generic FreeRTOS code available for everything and the AWS specific parts. So AWS IoT specific services include things like the job service and the shadow. So we also have helper functions for those. These are, or they're stored in a very same philosophy that each is in its own library. Each is in its own Git repository. We also have another package which is similar to the classic FreeRTOS distribution, but this is RTOS agnostic and actually tested on Linux. So this is, there's a very clear delineation here between FreeRTOS and anything which is Amazon specific. So despite what you read, that we do really try and focus on making sure that's the case. So I was going to talk about some of these use cases, but it's easier just to show some real world projects. So what does this distribution philosophy get us? Well, we have what we call the IoT reference integrations, featured integrations. These provide everything you need for mutually authenticated TLS connections, whatever you are connecting to. They also demonstrate over-the-air updates, over OTA, and they demonstrate how to securely store secrets like private keys. So I'm going to go through different ways in which being unopinionated helps. The first is a screenshot from GitHub. If you're familiar with the way they have submodules, you'll notice that all of these libraries are being brought into this project using Git submodules. So you can, in your project, keep that connection to Git, whether it's to the main line, so you can bring in the latest patches or the latest updates, or whether you're fixing on a long-term support version and you just want to bring in or see what the security updates are so that you can decide whether to bring them in or not. Note also, whilst I'm here, the number of libraries. I'll come back to that later. On the right, we are showing how being unopinionated enabled a partner to bring FreeRTOS libraries into a project that already existed. Not only that, but also not to change the directory structure either on the disk or in the project, so that it stayed in a way that their customers were familiar with. This is another way of bringing in the libraries. This is using Package Manager, which is web hosted. And here we are using a shell script and a command line within the kind of make files to bring the libraries in. And more familiar to this audience, also with much more kind of sophisticated package managers, which is what I would classify kind of the ESP IDF as. So FreeRTOS is in here as well. And incidentally, although we have lots of demos in the Git repo, you won't find many, if any, ESP32 demos, because the ESP IDF does that for you. It creates the projects in a much more sophisticated way and allows you to configure them and make sure they build and all that kind of thing. So for ESP32, this is probably the best way of obtaining the code. Okay then, so last kind of milestone is IoT Express link, right at the end of our timeline here. So to demonstrate the benefit of this, what I've shown here is kind of the user's view of one of those reference integrations, or it might be their own application code. Now remember I said we've got all those libraries which are required. TCP, TLS, MQTT, which is the protocol which is often used in IoT applications, HTTP clients, all of those different things are bundled in this diagram in this middleware libraries. And we try and make it as easy to use as possible by providing very simple APIs which, or encapsulating some of that functionality in what we call agents. Think of these as daemon tasks, daemon threads. So there's one for MQTT, which manages all the thread safety for you. The kind of core MQTT implementation is deliberately very small, doesn't have thread safety, but you can use it on an 8-bit device. If you're using it in a 32-bit, more sophisticated application, then this will handle the thread safety in multiple tasks, accessing multiple servers. Also, we have another agent for over-the-air updates. So this will download updates for you in the background and just tell you when there's one available that's been authenticated. I pick on these two deliberately because we'll come back to those as well. Here is a very common way of using these libraries. Here we have a microcontroller on which we are running all of this code. It's connected to a radio, and that radio gives the application access to whatever it is you're connecting to. Here I'm showing AWS IoT. So although we try and make these agents as easy to use as possible, it's still a technical product, right? You still have to be able to bring the C libraries in, build them, know how to configure them, get the kind of sequence of execution within your execution flow. So this is the scenario without ExpressLink. And if you watch on the next slide, what we do is move a lot of this or all of this middleware code over onto the radio itself to make what I kind of describe as a cloud modem. So now you don't have to do all those things with the C files like building and configuring. That's all done for you. It does the OTA for you, the update of the ExpressLink module itself and the application. It does the secure storage. You don't have to create a socket and a TLS context and connect to your server. It does all that for you. All you have to do now is write a string to the serial port, and that string is just AT connect to actually connect. So all of that complexity is completely abstracted away. You may even be able to use a smaller processor over here, one with less RAM. Now AWS only have the spec and the tests and reference integrations. We don't make these modules. These are made by partners, and I've got the URL down here to Espressif's ExpressLink module. Okay, so how are we applying what I've just spoken about to the roadmap moving forwards? I'm going to talk about everything on this timeline. There's no scale on this timeline deliberately because it's not absolute. We may even change the order in which these things come out. I'm going to start by talking about the things that have their labels under the line here, which are things which are being developed right now. So the first is generalizing the OTA agent. Now, when I showed this slide, which I've got in an inset here, you may have noticed that OTA was over on the AWS side. This is quite opinionated because it is connecting to the AWS IoT OTA service. So in the spirit of making things more applicable and less opinionated, this is being kind of broken apart now. So at the moment, you can do downloads over an MQTT streaming service or HTTP. If you've got your own over-the-air update mechanism, breaking it apart allows you to use that instead. You can do things like change when it looks for a download. At the moment, you just get notified when there is a new download available. Maybe you only want to do that at 2 in the morning, whatever. So making it less opinionated, which is one of the pros, so I've listed over here, more widely applicable. But one of the pros and cons is it's more flexible, right? It's more granular, more Git repos, perhaps with just the streaming, the individual streaming or download mechanisms in them. We will, of course, provide integrations which you can use. You probably have to put it together yourself if you wanted to actually change its behavior. Next is simplifying the MQTT agent. So incidentally, both the last slide I was showing and this one kind of demonstrate the tensions between different good intentions, if you like, in that making something less opinionated also can make it, kind of pains me to say, a little harder to use, but that's I suppose that's the truth. And with that, that's why I said more flexible is both a pro and a con. Here, we're looking at the MQTT agent update. This is the kind of contradiction between making it completely agnostic of the underlying operating system and the additional burden you put on the application writer, because if it's in its own agent task or thread, then naturally it's using some operating system functionality, and the application writer with this generic one has to kind of provide that themselves. So that's good from an unopinionated point of view, but we also want to make it easier to use. So we are creating a FreeRTOS specific version, and a lot of that additional code then moves inside the agent itself. And you have the choice then of which one you want to use. So I don't want to get too far into the weeds or too low level detail here, but it doesn't matter if you don't understand this. But when this is showing the MQTT publish function, if you pass in a callback function, then the application has to write that callback function, call the publish API. The API will return, and the server, depending on the quality of service you ask for, will then send back an acknowledgement, call the callback, and the application has to handle it. If you leave the callback as null, then all of that kind of signaling is handled completely inside. The application doesn't have to provide any kind of glue code at all. So yeah, pros here, there's less application code, and we've done this without changing the API. So no matter which version you use, the API is the same. And the con is, the contradiction here, if you like, is this particular version of the MQTT agent does have a dependency on FreeRTOS. So other things that are ongoing, this also gives me an opportunity to talk about how we use Git. When we want to change something in the core code, what we do is clone the Git repo, make the change in our personal repo, and then have a pull request to bring it back in. The pros of that are it keeps everything very clean in the core, the primary Git repo. The con of it is you've got to kind of follow the clones to see where the work is actually being done. So if you see a branch in the main repo, that's a very good indication that that branch contains a major feature enhancement that is intended to be merged into the main line. So here we're talking about the TCP stack. IPv4 and IPv6 code bases were different. IPv4 got all the love, and what we've done is refactored that a little bit and merged in the IPv6 code, because this is becoming more and more important, especially with things like the Matter protocol. And that, I think, it may even be merged now actually into the main line. We were waiting until all the security stuff had finished, and security reviews had finished, and also that the protocol testing had finished. I think last time I looked, it was on release candidate 3 or 4. We've also introduced a kind of enhanced or new port, depending on how you look at it, which enables us to hopefully improve or upgrade the security certifications. So CSIP is the security evaluation standard for IoT. And currently FreeRTOS has a level 2 certification. And our hope, our intention is to raise that to level 3. So very important to this audience next is the symmetric multiprocessing, or SMP. What we've done here, again, by the way, this is a screenshot from Git, and it's on a branch. So again, this is a major feature enhancement. So this will become FreeRTOS 11. And what we've done is taken symmetric multiprocessing forks of FreeRTOS from various different partners, consolidated them, and then we will merge that into the main line. So we've checked that it doesn't impact negatively those who are just using a single core as far as code size or runtime goes. Espressif have been a fantastic partner here, some major contributions, and I have to kind of hold my hand up here. This should have been merged into the main line already. The reason it hasn't was because I asked the team to get the security certification finished first, because changing a major version number partway through that can be problematic, and I think that kind of getting that done cleanly benefits everybody. But as soon as that's finished, then this will get merged in. Espressif again are a little bit ahead of this version here. I think the IDF version has more fine-grained locking for more performant and that kind of thing. But very soon these will all be one, and then we will be able to keep up and support in a much more active way. Right, so what is beyond that SMP FreeRTOS version 11? So this is kind of wrapping up here. We've looked at various different reasons that the FreeRTOS code base has evolved, and the kind of distribution methods have evolved over time. There's nothing here which is going to be surprising, right, for an open source project. It's what are the market trends, what are the pain points, etc. So when we come on to our intentions for version 12, this is future looking now. So that's why I say this is our intention. We've not done it yet, of course. So this is also tackling a pain point for people, and it may not be that pain point is directly applicable to a smaller subset of people. So hopefully I'll explain why this actually benefits the entire community rather than that smaller subset. And that is people who are taking FreeRTOS into developments that require some kind of safety certification. This includes teams inside Amazon, by the way, as well. So what we are going to do, or hoping to do, or intending to do, is make that much simpler. To do that, what we are going to do is, or intending to do, I should say, is remove a lot of the legacy code. So we've maintained backwards compatibility for 20 years. That means there's more than one way of doing things. That makes doing formal certifications much harder. So removing the legacy code, redesigning a few bits, but it's predominantly a refactoring. It's going to create a smaller, leaner code base. This is, I always say, the kind of forewarning that if and when we do this, we will break some of the backwards compatibility because there's only going to be one way of doing everything. So I'm giving, always say, this hasn't started yet, so you can have your opinions on this now. And the reason I say this benefits everybody is because, like I say, it'll be a clean start that we can then evolve for the next 20 years after this happens. So that's hence the title of the course. Sorry, the title of the presentation here. So with that, I'm going to invite everybody to get involved. I'm especially interested in your ideas for version 12. If you have safety projects which you are not able to talk about in like the public forum, which I've got the URL for on the screen here, then do feel free to get in touch with me directly. It's we do prefer to keep everything out in the open, but like I say, I do understand that some of these developments are you may not be able to, you may be constrained from talking about. But any other opinions on anything else, use cases, wishes? In fact, wishes you can have in GitHub, like kind of feature requests. You may also notice that we are working to improve transparency in GitHub. The roadmap will get published there as well. So I should say our intention is to publish the roadmap there as well. So some of the processes and practices are kind of being made more transparent there. And that is it. I hope that was useful for you. Thank you very much.
That's it, dear viewers. That was the first day of DevCon
23. Thank you for watching and asking your questions in the chat. Many thanks to the authors of the talks for sharing all this great content with us. The link to tomorrow's broadcast will be in the chat, and you can also find it on Espressif's YouTube channel.
All of today's talks will become available as separate videos on YouTube at some point in the next couple of days.
And we will upload presentations and link them in video descriptions as well.
So DevCon 23 continues tomorrow with another 12 talks, each followed by a live Q&A session. Goodbye for now. See you again tomorrow at 10 a.m. local time. Shall we go for a pint now?
Yeah, goodbye.
Good. See you tomorrow.